Est-ce que je peux demander pour?
Hi, Louis. Warning, this is a test.
welcome everyone. I hope you had some great days. Take this here. I have an echo somewhere. Now it should be good. Wonderful. Okay, welcome everyone to day 2 of our conference of Social Bridges. I hope you had some great, some time to digest yesterday's talks. Just as a brief recap, we have learned a lot yesterday as our speakers covered a wide range of perspectives and topics. In the first keynote, we had the pleasure to host Philipp Kallmeier from Freiburg, who talked about the multifaceted nature of trust in human-AI interactions. And then, just to name a few, we moved over to wine recommender systems. We had a game theoretical analysis of robotaxis and the limits of social machines. Our last keynote speaker of the day, Gordon Chang, closed day 1 with a fascinating talk on humanoid AI and artificial skin. So if you've missed the talk, one of the talks, or are keen to watch them again, you're free to do so and find them on the YouTube channel as a recorded live stream. And today will be not less exciting, but we hope to, have an equally impressive line of speakers lined up and talks. Our first keynote speaker, who is already with me, Michael Winikoff, will clear up some misconceptions about AI. And later, we are very happy to host Katie Winkler, our second keynote speaker of the day, to provide some insights into meaningful socially assistive robotics. Just as a brief reminder, you can find, if I can share it, the whole program and schedule on our website of Social Bridges. If you just Google it, and then you should be forward to the program where you can see all the different, so this was day 1, the keynote speakers, the topics, the abstracts, so free to browse around. This is day 2. If you want to join us live, you can do so under the Join Us Live button, and then here you can find the live stream where you probably ended up here now with us. So we're happy to have you. And also here, just to give you a hint, so here you can see where you can join, and the whiteboard, where you can leave messages, some food for thought, some links, and we also have a social gathering set up later during our lunch and coffee breaks, where we have, we'll host a hub of social interactions for people, who might be lacking some social interaction during our times. It's a great way to catch up with some speakers, ask some questions you were not, possible to ask during our sessions. And yes, so this is where you can find all the information. We'll post a link to the social sphere in the chat as well of the live stream. So just hang around there. This is also where you can put all the questions you have that come up to in the talks. And yes, we are very excited to have you. And with the organizational work out of the way, I'm very happy to welcome our first keynote speaker, Michael Winikoff. He is a professor and head of the School of Information Management at Victoria University of Wellington in New Zealand, and generally strives to create better software that enables intelligent agents. Today, he will unravel some myths and misconceptions about AI, such as the threat of human-level and superhuman AI. We are very happy to have you. If you can please switch on your audio so that people can hear you.
Hi, good evening, everyone.
Excellent.
Sorry, good morning at your end.
Yes. With that, you can try to share your screen if you want. Yes, that looks perfect.
Fantastic.
And I will give you a 5-minute warning when your time runs out. So roughly, as you know, you have 15 minutes for your talk, and then we have 10 minutes for questions. So when you're ready, please take it away.
Okay, thank you very much. It's a pleasure to be here, and it's, as always, these sort of online things, they're not quite as good. In this case, I'm also dealing with a sort of significant difference in time zones. It's about 8 o'clock in the evening over here. So welcome. Now, this talk is aimed at people who are not AI experts. And one of the issues with AI, artificial intelligence, is that the coverage in the mainstream media is often not so good and sometimes downright awful. So if you read newspapers, you may come across headlines and sentences like this, and you might be left with the impression that there is a robot apocalypse coming. In this case, reading a few more sentences, they're not coming to eliminate everything, they're just coming to take all of our jobs. Or you might have the impression that AI could potentially become billions of times smarter. And what does that mean? So in this talk, I'm going to address some of these myths of AI, things that get repeated and said in the media, but sometimes are just really wrong and also quite frustrating to people who work in the field. So hence the subtitle, what are the things that people who do work in the area of AI wish that were more broadly understood and appreciated. So some of the myths that you might have come across, often when you read newspaper articles about AI being deployed for a particular problem, you'll see phrases like, the researchers developed an AI that solved the problem. And in fact, that particular framing, as we'll talk about shortly, is problematic and misleading. You might be left with the impression that the AI research community is in a unified way working on developing some sort of generic purpose, single thing, and then in fact we're not that far away from human level intelligence, and that once we get to human level intelligence, super intelligence will follow fairly shortly. And there's this idea of a singularity you may have come across. And generally, you might be left with the impression that really intelligent machines are coming soon, and that's something that we should worry about. Now, all of these things are myths, and to try and understand why they are myths and what the reality is, in this talk, I'll be tackling a number of questions. So the first question to consider is, what is AI, which will address the first myth? And also alongside that, what is the discipline of artificial intelligence, which will clarify what the AI research community is doing and to what extent it is unified. And we'll also encounter a few other myths along the way. To answer the question of how close we are to human level artificial intelligence, the question we'll consider is, how hard is it to get to human level AI? The argument about superintelligence that I'll explain later on is in fact one that rests on a whole range of assumptions. And when you start articulating and questioning those assumptions, it turns out to be quite questionable. So a lot of those assumptions really don't stand up to scrutiny. And within the discipline of AI, people are not worried about intelligent machines developing their own agendas and going out and taking over the world. We are much more worried about the potential for stupid machines making really bad decisions. And one of the key things that comes back to is that is the lack of common sense, that a computer will do what it's programmed to do, and AI stretches the envelope in terms of things like machine learning, so you don't program them explicitly to do certain things, but there's still no ability for the machine to step back and say, what am I doing? Does that even make sense? So let's start by tackling the first question. What is artificial intelligence? So artificial intelligence is basically the idea that we're programming computers to do some sort of task that we would say would require intelligence if a human did that task. The sort of awkward phrasing there about normally requiring intelligence is just an attempt to sidestep and avoid the argument about whether machines can really think or really be intelligent. In the same way that birds fly, airplanes fly, they do it differently, but they both effectively traverse and fly through the air. So similarly, and we'll see examples later on, artificial intelligence, machines doing certain tasks that we would say require intelligence. If we were to do them, they might do those tasks very differently to how a human does them, but they still can perform tasks that should require intelligence. So that's what we call AI. And it's worth observing that this idea actually changes over time. So historically, there was a time decades ago when pathfinding, working out how to get from point A to point B, that's a task that we'd say requires intelligence. These days, we have very well defined and known algorithms for solving this, and it's not really considered part of the discipline of artificial intelligence. So that's what artificial intelligence is. Now, the discipline of AI, it's a topic of study in the same way that sociology or physics are disciplines as well. And the discipline of AI is concerned with developing techniques for allowing machines to do tasks that would normally require intelligence. And one of the two key points to take away is, first of all, is AI is not developing one master algorithm or one single technique. It's in fact developing lots and lots of different techniques, and different problems require different techniques. So if you're trying to play chess, for example, there are certain techniques that get used for that. If you're trying to recognize human faces and identify them, a different set of techniques. Coming back to this idea of the phrase of NAI, a more accurate phrase would be a software system that is using some techniques that have been developed by people working in this discipline. And sometimes it might use one technique, sometimes a system might have to use multiple techniques. So to give you a sense of what the discipline of AI looks like, this is a sort of partial map of the discipline. And you'll see that it's quite diverse. It includes topics like natural language processing, techniques for manipulating text in a language like German or English, speech recognition, taking audio and getting text out of it, planning, solving problems, representing knowledge, computer vision, robotics, and machine learning. And two additional myths that are worth pointing out now. One is that AI is not a unified field. If you go to a conference in artificial intelligence, perhaps HCI, the top conference in the area, you'll find a lot of very specialized work where people working, say, on planning would perhaps even struggle to understand the work that's being done in neural networks. So it's a fragmented field. It's not unified. The other myth that I have to also raise at this point is, and we'll see why this is shortly, there's a tendency in recent years to conflate AI and machine learning. One example of that, I recently saw an article where they were analysing where AI researchers would be happy to move, which countries they might prefer to work in. And what's problematic about that particular paper is they surveyed people who'd published in two particular conferences. Both conferences sit within that machine learning bubble. So the point is that the authors of that study looked at those two conferences and they said, we're representing the whole of AI with this. And of course, they're not. Machine learning is just one part of the discipline. Now, what I thought would be useful is to give a very, very quick history of the discipline. And I'm not doing this because the history in itself is that important or interesting, although I think it is, but because there are really interesting lessons that come out of it. So back in 1956 is when the discipline of AI is generally considered to have been founded and given its name. Early work in the discipline was quite optimistic. There was a real sense that AI was this problem that was really the essence of intelligence was logic and reasoning and problem solving. And if you could solve that, then everything else would be done and we'd have truly intelligent machines. And that shouldn't take too long. A lot of work was done, a lot of progress was made. And one of the key lessons that came out of that period was that reasoning alone is actually not enough. You also need knowledge. Then there was another sort of wave of development that was focused on knowledge. How do you represent knowledge? How do you reason with it? And one of the things that came out of that body of work was expert systems that can take a collection of symptoms and give a diagnosis. And again, one of the lessons that came out of that period was that reasoning and knowledge alone weren't quite enough. And for example, with robotics, it turns out to be too complex and too slow. So again, there was another wave that started to look at behavioral AI and the importance of perception and action, being able to interpret the environment and act in it. There's also been an ongoing thread about machine learning, and more recently, there's been a lot of focus on something called deep learning. So the reoccurring lesson here is that time and time again, there was optimism. There was a sense of intelligence is this, logic and reasoning say. If we solve it, it'll all be fine. We'll solve the whole problem. And as people learned more, there was this lesson that, oh, there's actually more to it than that. And that's a really important lesson to take away, that AI turns out to be harder than we think it is. There was optimism. It turns out that we are overly optimistic. So coming back to the more recent developments in AI, over the past decade or so, there's been a real explosion of interest and investment in AI. So you can see the level of investment really growing in this graph from 2010 to about 2015. And then from 2015 onwards, there's been continued growth. And I'll come back to why there's been this sudden growth in 2010. But one of the points to make here is that this is where we get this additional myth that AI is a very young field. There's a lot of attention that's come to the field in the last decade. And of course, the reality is that it's actually around 65 years old. Now, the reason why there's been a lot of attention to AI over the last decade, and why a couple of slides back, I sort of had machine learning, and then within that neural networks, and within that the sub area of deep learning, is that there's been a lot of effort, a lot of attention paid to deep learning. So I'm going to very briefly talk about deep learning. And again, it's not so much because I want to talk about deep learning, but because it's also a really important lesson from some of the weaknesses of deep learning. So what is deep learning? It's basically the idea that it's a form of a neural network. A neural network is a software simulation of a mathematical model that's inspired by certain aspects of the human brain. So it's not simulating a human brain. It's simulating this idea of neurons that can fire, and they're connected to other neurons, and they might trigger other neurons. So you can think of this as a network of nodes, and there's an algorithm for how nodes fire or not and affect other nodes. So it's an abstract mathematical model inspired loosely by certain characteristics of the human brain. The word deep in deep learning refers to the sort of number of layers of these simulated networks. And the reason why deep learning has attracted so much interest is that over the past decade or so, it's been able to demonstrate dramatic improvements in the ability of computers to perform certain tasks. And some of these improvements have come from developments in the techniques and algorithms. Some of them have come from computing power, really fast computers, and the availability of really large data sets. So let me give you a few quick examples. Speech recognition, this goes up to 2017, but again, you can see dramatic improvement from 2010 onwards. And just as an aside, going from 85% accuracy to 95 doesn't just mean that we're now at sort of human level performance on this task, but it also is quite significant. It means that instead of 1 in every 6 words being wrong, 1 in every 20 words is wrong. And that makes a difference to the usability. And if we look at what's happened more recently, you can see that, okay, this is actually a different task. So this is identifying objects. And again, the exact details aren't that important. The point is, for this task, again, there's been significant improvement. And for this task, computers are now able to actually outperform humans. However, these techniques are not good for everything. One example is a certain form of visual question answering that, in fact, there's been some improvement, but it's still struggling to reach human level performance. So deep learning is good for certain tasks, especially things like perception, learning simple rules, playing certain video games. It's not so good at other things, and it has 2 particular weaknesses. One is that it's a bit of an art form to engineer these deep learning neural networks to perform a certain task. There are techniques now being developed for how we can understand how these networks work, and it's difficult to provide strong guarantees that they won't break down. And you might recall earlier that I said that, remember the birds and the planes? AI can perform certain tasks, and sometimes it does it in a very different way to how we as humans would do that. And one very nice way of illustrating this is these images. So these were carefully engineered as adversarial images. So the context is there was a particular piece of software. It was trained to recognize certain images like electric guitars and starfish. Then these adversarial images were engineered, and in each of these cases, when the network was presented with one of these images, it would come back and it would say, that third one, I'm 99% sure that's a baseball. So it had a very high degree of confidence that it was recognizing a baseball in that third image. And what this really highlights is that the way that the neural network had learned to recognize baseballs was very different to how a human would do it. So if I was looking for a baseball, you'd look for something small, round, white, and perhaps with a bit of red. The network obviously learned to identify particular patterns and textures. Similarly, that electric guitar, starfish, and king penguin. And in fact, networks can be fooled, and they can be fooled in quite dangerous ways. So that image in the middle of the slide there is a stop sign. The image on the right side, the network recognizes as being a 45 speed limit, even though, of course, it is just a slightly manipulated stop sign. So that's one of the issues with deep learning and with certain other AI techniques, is they can sometimes be operating in a very different way to a human and make mistakes that are completely alien and completely, in some cases, unexpected. So this brings us to where are we today? So today we have a broad range of techniques that have been developed by the AI research community over the many decades, and there are a whole range of tasks that we can get computers to perform effectively. So facial recognition, solving puzzles during logistics, playing certain board games at superhuman level, things like chess, checkers, more recently Go, navigating, recommending products, translating between languages reasonably well, and so on. So that hopefully addresses the first two myths. So what is AI? It's not a thing, it's just a toolbox of techniques that can be applied to solve different problems. Different techniques are used for different problems. The discipline of AI is diverse, somewhat fragmented, and it's certainly not just machine learning. And let's now turn to the next question. And the next few questions have us looking ahead into the future. So, human level AI, how close is that? Well, to answer that, we really need to step back and say, how hard is it to achieve human level artificial intelligence? Now, there's a saying that's sometimes used in research and in project management that the first 90% of the problem takes 90% of the time, and the last 10% of the problem takes the other 90% of the time. The point being that sometimes we think we've tackled most of the problem, but in fact, it actually turns out there's a lot more to do than we thought. And that was certainly a recurring lesson in the discipline of AI over the decades. And if we think about, for example, self-driving cars, we have cars on the road today that can identify obstacles generally reasonably well, obey road rules, and navigate to their destination. Now, we might think, okay, we've got cars on the road, surely we can't be that far from having self-driving cars that can be fully autonomous. But it actually turns out that that last 10% is actually really quite hard and quite substantial. So let me give you an example. Suppose that you're driving along and you come around a corner, turn, and then in front of you there is a truck parked, double parked with flashing lights, and people are unloading things from the truck. What should you do? Should you wait patiently? Maybe they'll be there for quite a while. Maybe you'll annoy the people behind you. Or should you overtake, which may be illegal, it may be unsafe. So to make those sorts of decisions, it's not just about identifying obstacles and following the road. You need to have an understanding of human behavior. They're performing a task, they're unloading, how long are they likely to take? You need to have an understanding of what other drivers might expect you to do in this situation. So those sorts of things suddenly are not just about the hard problem of identifying obstacles in a complex scene and following a road, they're about the much harder problem of understanding human norms, human behaviors, and when it's appropriate to perhaps break the law, to overtake illegally. So to understand how close we are to achieving things like self-driving cars, let alone full-blown general purpose human level AI, we need to have an understanding of how hard these tasks are to do. Another example is real-time audio translation. Again, we have tools today that can do that, but doing it really well, in fact, turns out to not just require matching words and matching sentences and learning from the vast amount of text that's online, but it actually requires understanding of human culture, human history, and even perhaps human emotion. So if you have a piece of text and you want to translate it reliably and capture what it's saying for an audience in a different language, you need to understand what it actually means in the original language, in the original social context, cultural context, and then replicate that. So let me give you an example of that. I suspect that this conference has a lot of German speakers in the audience. So there's an original piece of text there in German and two translations, one by machine, one by a human. I'll give you a few seconds to read that. So hopefully you can see fairly clearly which one's the human translation. It's the middle paragraph. But the point here is that the bottom translation is pretty good, but it loses meaning in a number of places, and some of that's fairly subtle. So, for example, that very last sentence, and scientists did not question anyway, the original text is talking about female scholars, which in fact is crucial for the meaning of what it's saying. So that's an example where translation can sometimes get things wrong because it's missing the context. And of course, to translate some of the concepts from German, sometimes you have to actually explain them because they're not known. So for example, the idea of what is a professor in the German system might be different to what a professor is, say, in the North American academic system. So to get a sense of how close we are to human level AI, we need to understand what things are hard, what things are easy, and how hard is full-blown human level intelligence. So let me give you a few examples of tasks and how easy and hard they are. Logical reasoning, something that was tackled back at the dawn of the discipline, turns out to be easy, relatively easy to formalize and program. The but there is, it doesn't actually scale up to larger problems. You have combinatorial explosion. On the other hand, physical sensing and locomotion, perceiving an environment like robots have to do and navigating around it, actually turns out to be quite hard. Understanding humans, relating to them is very hard. And common sense, that sort of body of knowledge that allows me to know that if I take an egg and let go, it will fall, it will break, and it will make a mess. That's also very, very hard. So one point here is that the tasks vary from easy to sometimes very hard or even extremely hard. And I'll come back to the other point a bit later on, that sometimes working out which is not at all obvious. So I want to quickly digress to talk about creativity, because that's also something that you'll come across in the media. Can computers be creative? Can they create new things? So let's give the example of composing music. Now, in fact, this is something that I do as a hobby, so I do feel that I can talk about this. How hard would it be to get a computer to compose music? Well, like a lot of questions, the answer is it depends. Creating a new piece of music is actually really easy if you're just generating random notes. And if you set it up with, say, a nice pentatonic scale, it'll probably sound listenable and may actually work. It would be new, but it's not particularly necessarily well structured. Creating a piece of music that follows appropriate musical structures, perhaps chorus and verse with the appropriate amount of repetition, that's harder, but it's not that incredibly hard. What is hard though is having the computer be able to take something that is generated and assess whether it is actually a good piece of music or not. And for example, taking a poem, reading it, assessing the mood of the poem and setting it in the way that reinforces that mood, that's very, very hard. And it's probably what we call AI complete. In other words, to do that, you probably need to have a computer system that is equivalent to a human, that can understand the meaning of text, understand emotions, and try and replicate them. And before I move on, one thing that appears a lot in the media is stories of the form, here's a piece of music, of art, or of text that a computer created. And if you delve into the article or dig into the backstory, almost invariably what's really going on is humans played a role in setting up the computer, deciding, for example, what scales to use, what musical structure. So it's not just the computer creating things completely on its own from a blank slate, but then they'll hit the button and generate a number of things, and a human will then look at them and go, oh, that one's a bit boring, but that one looks cool, I'll select that one. So really, a better way of framing this, hey, computer created a new piece of art, is we set it up so that it has the background to do that. We hit the button and then a human came along and did which one of these is good. So selected by a human is actually quite crucial. So the key points in terms of this difficulty thing is that some things are easy, some are hard, and some are very, very hard. So the range of difficulty is quite a wide one. Some of these things, like how can you get a computer to listen to music and say, yes, that's good, that's not so good, that's really difficult. The other key thing, and I've hinted at this already, is that it's not easy to know what things are easy and what things are hard. And back at the dawn of AI, the focus was on logical reasoning because the feeling was that's the hardest thing. All this perception stuff, that's fairly easy. And what that reflected was a human-centric assessment. We as humans find perception fairly easy to do. We're well designed to do that, if you would. We find navigating around a room fairly easy to do. Logical puzzles, quite challenging. For computers, it's actually the other way around. Just because we humans find navigating and perceiving things easy doesn't mean it really is easy. It just means we're really good at it. Conversely, just because we find logical puzzles hard doesn't mean it's, or mathematics or algebra, doesn't mean it's really hard. It just means that it's not a natural thing for humans to do. So our assessment of what's easy and what's hard is colored by our own view of what's easy or hard for us. And that sometimes misleads us to think, well, this is a really hard problem, whereas in fact, it's not. The really hard problem might be something different. So coming to human level general intelligence, two bits of terminology. So weak or narrow AI is what I talked about in the very early slide, getting a computer to do something that if a human would be to perform that particular task, would say it required intelligence. That's something that clearly is being done. There are a whole range of tasks that computers perform and has been for a while, but it's narrow. So a computer program that's been developed to play chess, it's not going to be recognizing faces, not at the very least without substantial reconfiguration and training. Strong AI is general purpose intelligence. It's a single system that can do anything that a human could do. And that's something that is not here. We don't have any examples of that, but we know that it's possible because we humans are examples of that. On that scale of easy, hard, very hard, that's something that's extremely hard. And I'll come back to what I mean by extremely hard a bit shortly. Now, how do we know, by the way, if human intelligence has been achieved? There's the idea of the Turing test, that you can put a human in a room, put a computer in a room, have a conversation with each of them through a typewriter. And if you can't reliably pick which one's the human and which one's the computer, then the computer has passed the test. And the key point is that it's really meant as a sort of really hard task because you can ask all sorts of questions. You could say, make up a poem for me, or here are 3 jokes, which one is actually funny? Here's a recent transcript from a cutting-edge AI system. And I'll give you a few seconds to read in a second, but one of the points here is that modern day natural language processing techniques can string together sentences that are grammatically correct and flow in terms of topic, and that's really impressive. What they don't have, though, is an actual understanding of what's being asked that allows them to provide appropriate answers. So have a quick read through that. Okay, so as you can see, it's sensible grammatically, the topic flows reasonably well, but in terms of the answers being sensible, they're clearly not. And I think this particular system is clearly not passing the Turing test. So, coming back to how hard is it to achieve human level AI? So there's a lot on this slide. Let me quickly talk through it. So the chart, the big chart in the middle there, comes from a survey that Professor Toby Walsh did. And what he did is he went out to a whole bunch of people and asked them, by what year do you think there will be a 50% chance that we have human level machine intelligence? And those curves are cumulative. So the top curve there says that by the year 2040, roughly 50% of the respondents thought that by 2040 or earlier, there'd be a 50% chance of human level machine intelligence. The key finding here, though, is that that top yellow line is asking the general public. When Toby asked people who worked in the discipline of AI, they were significantly more pessimistic. They expected slower progress. So the point by which the general public thinks 50%, well, half of the general public thinks by then 50% chance of machine achieving human level intelligence is about 2040. For people who work in the discipline of AI, that's more like 2062. And in fact, Toby went on to use that as part of the title for his book that talks about AI. So the point here is that Experts, the ones who do understand the difficulty of the problem, are more pessimistic. They're saying, no, it's actually really hard. It'll take us longer. It's also worth noting that, in fact, most AI researchers, if you go to conferences on AI and look at what they're working on, they're not trying to achieve general purpose human level intelligence. The vast amount of work in the discipline is focused on improving particular techniques for solving particular narrow problems. And that's not a criticism. I mean, solving narrow problems can be enormously powerful and enormously useful. If you can allocate resources more efficiently across the supply chain, say, that can have enormous benefits. If you can predict the outcome of chemical interactions and develop new drugs, again, that can be huge. So AI is generally, especially with the recent boom, is making an enormous difference and is expected to make an even bigger difference to human well-being, to economic and other forms of well-being. So most AI researchers are not even looking at trying to achieve general purpose human level intelligence. And furthermore, getting from where we are today to general purpose human level machine intelligence, the current approaches and techniques that we have, it's not even clear that they're adequate. It's not just a matter of taking all the toolbox of techniques that we have and extending them and building on them incrementally. We need potentially completely different new techniques, and we don't know what they are. Now, it's possible that tomorrow somebody will wake up and have this brilliant vision and say, if we do things this way, it pulls everything together and suddenly that solves the problem. I think it's fair to say that most people in the field don't expect that there's a sort of single easy idea that will solve AI. So it's really hard. We're not expecting it to be solved anytime soon, and we're not in fact really sure how you would go about a path towards human level machine intelligence. So that's the human level AI. It's not close and it's extremely hard. The next headline that we actually started with was this idea that AI might potentially be billions of times smarter than humans. So the person they interviewed actually, I think, said it could be. The headline, of course, made that more certain and stronger by saying it will be billions of times smarter than humans. Now, this is a good time to bring a quote from Professor Michael Wooldridge, who is very much an AI researcher, a very highly regarded one. And he writes that it is a source of great personal frustration to him that the press are happy to give airtime to views on AI that he considers to be ill-informed at best and lunatic fringe at worst. So one crucial takeaway message that I would really like to stress when you're reading articles in the media where the reporter has interviewed someone about artificial intelligence, always ask the question, who have they interviewed and what is their expertise? And if it's somebody talking about superintelligence, do they actually have expertise in AI, or are they someone with expertise in a different domain? Maybe they're a physicist or a philosopher or a successful entrepreneur. And just to highlight how ridiculous it is that we're asking, say, entrepreneurs about AI, if we had an article that was about the prospects for curing cancer, and there were comments there from an entrepreneur or from a philosopher about, well, we're progressing and we're expecting to have a cure for all forms of cancer in the next 5 years, I think we'd be extremely skeptical and we'd be saying, well, what do the medical researchers say? Because we recognize that cancer is a complicated collection of diseases and that you really do need expertise to talk about it sensibly. And that's also true for AI. As you might guess, the quote there that AI can be billions of times smarter than humans is not coming from somebody who has relevant expertise. So, billions of times smarter, superintelligence, what are we talking about? So quick definition, superintelligence is any intellect that greatly exceeds the cognitive performance of humans in virtually all domains of interest. And when you start reading about that, one of the other ideas that comes up is this idea of a singularity, which is a hand-wavy argument that when we develop human-level general purpose intelligence, which remember is not expected to be anytime soon, what happens then? Well, the machines are like general purpose. So what can they do? They can design new machines that are even better. And computers are getting faster as well. So they'll design faster, better machines. Those machines will design even better machines. And you get this self-improvement kicking off that grows exponentially. So before you know it, we have machines that are billions of times smarter than humans. So that's the hand-wavy singularity argument for why superintelligence is going to happen quite soon and very quickly. Now, like a lot of hand-wavy arguments, when you dig into it, it rests on a number of assumptions, and these assumptions are, at the very least, questionable. So, first of all, there's the assumption that you can draw this graph with intelligence as one axis and time as the other. So intelligence is the single dimensional thing. It also assumes that there's no limit to intelligence, that you can have such a thing as billions of times faster. There's a bit of an assumption that faster is smarter. So as computers get faster and faster, they will also get smarter. And of course, the key assumption is that self-improvement is possible indefinitely, and that it kicks in at more or less human level. So if we had a general purpose human level AI, that's when it could start doing significant self-improvement and kickstart this whole process. And none of these assumptions actually really stand up to scrutiny. So we know that intelligence is not one-dimensional. I'm sure you can think of people who are really good at certain types of tasks and much less good at other types of tasks. And we also have no reason to assume that there are no limits to intelligence. There are limits to everything in the physical world. The speed of light is a relevant limit. So it's highly unlikely that it's even possible to have something that's billions of times smarter than a human. We don't know where the limit is. It may be that the limit is sort of 10 times smarter, whatever that even means. It might be that 2 or 3 times smarter is about the limit. The assumption that faster equals smarter can easily be dispelled by imagining a dog that can think 5 times as fast as a normal dog. They may be really good at running around and finding things, but they're not going to be playing chess. So speed is not necessarily intelligence. And finally, in terms of self-improvement, we've actually had decades of humans, in fact, really smart humans, working on AI. And we're not even close to human level AI. So if we suddenly had human level AI magically appear today, it's quite possible that that human level AI would be working for another 60 years in order to even substantially improve itself. Human level AI is really, really hard, and that's something that people outside the field don't really appreciate. So if I can summarize this, again, quoting Michael Wooldridge in his book, he has a section titled "The Singularity is Bullshit," which I think summarizes quite nicely his perspective. So we've seen that human level AI is not something that we need to worry about in the near future. The superintelligence is not something that we really need to worry about. However, AI does raise a number of concerns. So the real concerns are not superintelligence, they're things like algorithmic bias, unemployment, autonomous weapons, and a whole bunch of other things. Diversity in the discipline of AI is still quite strongly male-dominated and not ethnically diverse. Fake news, facial recognition, a whole bunch of ways in which AI provides tools, and then those tools can be abused or misused. Now, I don't have a lot of time to talk about all of these, but I think it is useful to very quickly touch on a few of them just to give you a sense of what's the issue and what's the concern. And I apologize if these are things you've already come across. So algorithmic bias, how can an algorithm be biased? Can an algorithm be racist or sexist? Well, if the algorithm is learning from data, then it can certainly pick up all sorts of biases from the underlying data. So let me give you an example to illustrate. This is a passage, a collection of sentences in Hungarian. Why Hungarian? Because Hungarian doesn't have a notion of gender. So you'll see all of these start with a O, szép, okos, and so on. I apologize for my pronunciation. If you run this sentence through Google Translate, you get the following result. She is beautiful, he is clever. She's a cleaner, he's a politician. He makes a lot of money, he's a professor, she's an assistant. What's going on here is that Google Translate relies and learns from the vast body of text that's out there. And statistically speaking, you are much more likely to see he is a politician than she is a politician. So the translation reflects the biases that exist in written text, which in turn reflect the historical biases that exist in society. Most countries, if you look at the collection of politicians, there are more male politicians than female politicians. So if I tell you that someone is a politician, statistically speaking, it may be the right thing to sort of say, well, if I have to pick between he or she, maybe I'll pick a he. So the point here is that biases can be picked up. Now, the right thing, of course, to do is simply to not assume. And to give Google a bit of credit, if you just take the first one and run it through Google Translate, it will come back and say, hey, Hungarian doesn't specify gender. I could translate this in 2 different ways. Which one do you want? There is room for improvement of the translation, but the point is that algorithms can pick up a wide range of biases from the underlying data. And even worse, if algorithms are used in certain ways, that can lead to negative loops. A simple example there is, imagine using crime statistics to decide where do you allocate police patrols. Well, where would you put them? Where there's more crime reported. But of course, the more police you put into an area, the more likely there is to be even more crime reported because that area is under more scrutiny. Conversely, if there's an area that historically maybe hasn't had very much crime reported and you under patrol that area, you're even less likely to find more crime there. So that sort of reinforces with a negative feedback loop that sort of just strengthens the bias. And the challenge with algorithmic bias is that it's not easy to fix. Sometimes you can remove information from input data, but there are still proxies for that data. So for example, if you have a system that's trying to recommend loans or insurance, you might say, well, we don't want to tell this system about the race or the ethnicity of the people applying because that should make a difference. But in fact, machine learning might find that there are other things that you can use as a proxy. So for example, in the US, postcode is a pretty good proxy for ethnic identification. And probably the best fix for algorithmic bias is to be aware that it can happen, be aware that it's not that easy to fix, and therefore it's a question of where do you use machine learning, in what ways, how much oversight is there, and what ability is there to challenge decisions. Which another thing that's important is being able to explain why a system made certain decisions or recommendations, so you can understand what factors fed into it. The second issue is AI-created unemployment. And there are 2 arguments that I made in this space. One of them is an abstract economics argument, which is, yeah, we've heard this all before and it hasn't happened. So we've had previous waves of automation and there's not been mass unemployment. And the high-level economic argument is that more automation results in more wealth because its production of goods and services becomes more efficient. And if there's more wealth, that means there's more demand for goods and services. And that demand then translates into actually more jobs for creating those goods and services. But of course, one thing that argument doesn't consider is the wealth distribution. And if automation means that wealth gets disproportionately concentrated into certain subgroups of the population, that can be unhealthy for the society and it can undermine this argument. So if instead of having a whole collection of people who are reasonably affluent and spend money, they end up becoming poorer, and a tiny sliver of the population gets a lot of money, they won't spend as much. The counter argument is, hang on, but this time it might be different. If we can potentially automate all the tasks that a human might do, then why would you employ a human? Machines are going to be more reliable. And the analogy there is sort of peak horse, the idea that at some point in history, there were a lot of horses pulling around things, and once the internal combustion engine, cars and so on came around, those jobs disappeared and we now have much, much fewer horses. However, as we know, human-level AI is not that close, and there are a few factors that sort of mitigate this potential for widespread unemployment. One is that automation is most likely affecting parts of jobs, not whole jobs. And the other one is that if it occurs over a reasonably long time period, then there is naturally adaptation that occurs in the job market. Now, of course, just because something is possible to be automated doesn't mean that it's financially viable, or it may not be acceptable to automate it. There are some things where we'd really want humans to do, even if a robot could potentially do it. For example, I would probably feel uncomfortable having a robot cut my hair. It's often pointed out that technology doesn't just destroy certain jobs, it also creates new jobs. So the bottom line in this sort of unemployment issue is that in fact the jury is still out. We don't know how this will play out. It may be that certain occupations do get replaced relatively quickly. So driving might be an example of that, where if self-driving trucks do take to the highways in the next 5-10 years, that may result in significant unemployment in that sector. But it's too early to tell. And there are, of course, things that computers don't do well because they're really challenging to do well, and they're the things where humans are still going to be most needed. So abstraction and deep reasoning, being able to read something and really understand it, creativity, which we've talked about earlier, and dealing with people, communicating effectively, understanding people, and having emotional intelligence. The third issue that I wanted to flag, which is a sort of challenge and threat from AI, is autonomous weapons, sometimes known as killer robots. Now, almost all media articles about this topic, unfortunately, tend to have a picture of the robot from the Terminator movies, and that's misleading because that's not what we're talking about. We're not talking about highly sophisticated devices that can plan their agendas and have sophisticated goals or are humanoid. We're talking about something much, much simpler that does not require strong AI and can be done today. So imagine a small drone with sensors and cameras. It can navigate, it can recognize faces, we know how to do that, and it can identify people and fly up to them and then detonate. That stuff can be done potentially today, and if it is done, it's incredibly dangerous. Pardon me. There's a video that's well worth watching that's sort of, it's done like a short documentary. It talks about how this plays out. But basically the key concerns with this technology is that it's a weapon of mass destruction. Technology tends to become cheaper over time, and if this stuff gets developed and starts getting deployed, it'll make its way into the black market. It will become widely available. So a country or even an organization could potentially buy up a whole pile of these things. So it's a weapon of mass destruction, and it's a precision weapon. If you detonate a bomb, you're affecting everyone in that area. If you send a swarm of these things into a university or a senate, you can set them up to identify particular people based on who those people are, based on their ethnicity, based on what Facebook groups they belong to. So it's a precise weapon, and it's an amplifier. I said earlier, countries could have a lot of these things. Individuals could deploy them, and that's the really scary thing. It's not that nation states might start using these in far off wars. It's that individuals will start using them as weapons of terror. And of course, nation states could also use them as weapons of oppression against their own people. So that's a really big concern, and there's a move to try and get these things preemptively banned before they get developed and become widespread. And there are a whole bunch of other issues as well, which I don't really have that much time to talk about, and I suspect others will talk about them as well. So things like accountability, responsibility, robustness, and transparency. Can we understand why a particular piece of technology is doing what it's doing? Can we then have some way of saying, well, it's doing something wrong, who's responsible for that and who becomes accountable if it's a problem? And are these machines going to be reliable? The bottom line is that AI is a powerful technology, collection of techniques, and we need to use it wisely and develop our policies around it carefully. And one of the things that's crucial in doing that is that that's not something for technologists to come along and say, this is how we should be using AI. This is a question for society, for the philosophers, the sociologists, the politicians, and for everyone. But in order to have a good, sensible discussion around AI and its uses, it needs to be founded in accurate information. So some of these myths are problematic because they take us away from where the issues really are, and they lead to unfounded discussions. So myths like there is such a thing as an AI, and the AI community is working in a unified way to develop an AI, and it's a really young field, but human level AI is really close, and then we'll have super intelligence and we have to worry about that. That's not helpful. And as we saw, AI, which is much more than just machine learning, is in fact diverse. specialized. It's a discipline providing a toolbox of techniques that's been around for 65 years or so, and that human level AI is not something that we believe is imminent. And the real worry is stupid machines doing things that in a bad way because they just don't know better, and misuse of AI. And that's something that is up to all of us to be part of the conversation and to develop appropriate responses, practices, and legislation. So I'll finish there. I should have also said at the outset, I'm very happy to share my slides, and I've got a few recommended books and articles there as well. So thank you very much. I'm happy to take questions.
Thank you so much for that enlightening talk on kind of what AI means to a different field, bringing that perspective to this interdisciplinary audience. I think that was very helpful, to clarify the notion of AI. And with that, I would just segue into the first question. Do you think we need to reformulate the notion of AI to move it away from this discipline name and capture the meaningful notion of intelligence?
Do you mean the name of the discipline?
Yes, I think what the question means is kind of right now we use AI to capture this wide range of discipline, the slide you had in the beginning. So should we then actually try to reformulate that concept and apply it, to mean actually, intelligent behavior, what is meant like compared to human behavior? So we would just use, machine learning or algorithms instead of AI.
Yeah, I mean, the other term that gets used sometimes is machine intelligence, which is pretty close. I think the term AI I don't see as problematic because, I mean, the key thing is that we are trying to develop techniques for machines to be able to exhibit intelligence, and it's narrow intelligence, and perhaps we could try and communicate that better. But it is machines. It is, I mean, maybe we could use machine intelligence than artificial intelligence. But it's still how do we get machines to behave in ways that are intelligent on particular tasks?
Yeah, thank you. The next question asks, what's harder, beating a human in a computer game or collaborating with a human in a computer game?
I would say collaborating is harder because to do collaboration effectively, you have to understand what the other person might be doing and perhaps anticipate what they're doing. And conversely, for a human to be able to collaborate with a machine, the human needs to be able to understand what the machine is doing, which either means the machine has to have some way of communicating things like what it's about to do and why. And also it may mean that you want the machine to behave in a human-like way. So it doesn't behave in a really odd way. And for example, one of the things that's been observed about machines playing chess or machines playing Go is they sometimes play moves that you think that's a really weird move. No human would make that. It might be a really good move, but it's a non-human-like move. And if you're doing collaborative things, that's not really helpful. If you're trying to work with a team and your teammate does something really weird, it might be the right thing, but if there's no explanation or communication to go with that, it can lead to misunderstandings.
Yeah, wonderful. Thank you. I remember this weird Go move the system played, and then everyone was puzzled. It's like, oh, why did it move? So I can relate. The next question is linked on, was connected to it. I think it asks, why is it important to understand how hard a problem is to solve it sufficiently? We don't need to understand what 8% of the work looks like to get started and achieve the work.
Why it's useful to understand how hard something is to get a sense of when do you anticipate it might be solved. So you can certainly get started. I mean, if something's too hard, then you might want to think, really, do I want to tackle this? Am I going to get anywhere in the next 10 years? And if you're happy to invest 10 years and not have much to show for it or incremental progress, that might be fine. But in terms of saying, right, we're going to have this problem solved in 5 years, or we're going to have this problem solved in 20 years, that's where it matters, is about that expectation. And a good example of that is self-driving cars, where again, companies that are developing these things have put out a whole sequence of statements over the years that have been quite optimistic and that have been questioned by people within the field. There was one particularly well-known statement that was made about there will be this many cars by the end of this year, and a couple of well-known figures in the AI community said, if that's true, we will personally eat those cars. And of course, they didn't have to eat any cars.
Okay, that would be quite interesting to see. Fair enough. Then the next question asks, okay, should AI-powered systems be unconditionally benevolent, cooperative, and submissive?
So the issue with that is that, first of all, it's not clear how you would define benevolent, because often in the real world you get trade-offs. So if you have a situation where an AI system has to behave in a way that it's not going to make everyone happy, so one person prefers option A, another person prefers option B, what is the benevolent option? So it comes back also to Asimov's laws, which sound really nice on paper, but they just are not implementable. And there's two reasons why they're not implementable. One is that they require a lot of being able to reason and interpret situations and common sense that we don't have. We don't even know how to begin to get the machines to do that. And the other issue is it assumes that you can anticipate the future and predict forward and work out what will happen. And machines are not, AI is not magic. It can't foresee the future. So similar with self-driving cars and the trolley problem, there's a whole body of work that says, well, what should a car do if it sort of sees a pedestrian, it has the option of crashing or veering and hitting an elderly grandmother with a cat? And you can set up all sorts of trade-offs and try and tease out what humans' ethical decision-making. A car in practice is not going to have that degree of perception to identify all the things or the time to really think about it. It's just going to, if it suddenly sees an obstacle, you slam off the brakes. That's about all you can do. So.
With that, I think AI is not magic. I think we can leave it there. We reached our limit. Thank you so much for being here and giving the talk. It was quite fascinating, and I already see that our next speaker is waiting as well. So again, very well, thank you again. And there are a couple of questions in the chat. So if you move on to the live stream, you can see them there. People are probably interesting to engage with you there. Thank you so much. And with that, we move on to our next speaker, very own Maximilian Moll, who is a postdoctoral researcher at the University for the Bundeswehr in Munich. And today he will show us where the difference between human and machine lie, and therefore he will focus and compare learning behavior of both systems. Max, are you there? Can you hear us?
Yes, I just came in. Thanks for the introduction.
Wonderful. You can try to share your slides, and then we can get going.
Exactly. Now this should be working. At least
yes, we can see it. Wonderful.
It did. So off we go. Well, thanks a lot. It will be difficult to follow a keynote like that, which was absolutely brilliant. And I want to try and follow on in a fairly similar spirit, in the sense that I am an AI researcher in the strictest sense. And what I'm going to present to you is a collaboration with Merle, who has been organizing or has been behind this conference a lot. And it was quite interesting because while I am in a field that, as we will see in a moment, could be considered a bit closer to human-like learning than many others, during our collaboration, it became clear how different the two fields of research actually are. But before I'm going to go into the details of this, let me give you some impressions of what is going to await you. And I'm going to show you a video of the experiment that our participants had to do and invite you to follow along with this. You'll be seeing two video clips, and then you have to decide for one or the other. Very, very simple, and you'll be informed whether your decision is correct or not. And your goal is, after some time, to figure out which decision is going to be correct. Now, mastering this is one thing, but I invite you to think for a moment how you would go about making progress in this and getting better in this. Okay, there we go. Now, the first thing you might have noticed is that the participant we videoed here wasn't particularly successful, at least at the beginning. To show maybe some of the difficulties behind this, before I tell you all about the background, if you look very closely at the next two examples, you can see that here we have waving followed by clapping, which was actually incorrect if we clicked on video 1, followed by waving and clapping, which was incorrect by clicking on video number 2. In other words, giving different answers to the same problem still was presented as being incorrect. The reasoning behind this is that this is a probabilistic task. In other words, in a given setting or for a given pairing, you'll always only be right with a certain probability instead of with certainty. And that makes the learning process just a bit more difficult. However, if you might have missed that you've seen a couple of pairings more than once in this, it might start to show that this task, even though it's fairly simple, as we will see in a moment, is not as easy as it appears. We then had the very same task, this time with listening to audio snippets instead of watching small videos. I'll show you an example of this as well. And you might have noticed certain differences in listening to this one compared to watching the other one. For example, you might have realized that this plopping sound, at least for me that is the case, was much easier to recognize again than many of the video bits we've seen before. Now, why am I presenting two of these in two different sensory perceptions when I want to talk about comparing learning between humans and AI? The reason is that we extended this a little bit further and compared learning by a computer versus learning for human based on different senses. Because along the way, we can examine whether we make differences in learning with different senses. And quite interestingly, the computer doesn't, because the computer, at least as we will see in a moment, in the sense that we are going to look at now, doesn't make a difference in how the information enters its system. And so let me start off by talking about the computer side of things. Now, I like to start with this picture when talking about that, even though it does not look like I'm talking about the computer side. Once I add the second picture into this, it becomes a bit more obvious. We've seen Alan Turing, who is depicted on the right-hand side here, in the talk before. Now he's a bit older in this picture. But the point is that the area of research I'm going to talk about is actually being traced back to these two gentlemen. Pavlov on the left-hand side, I don't think needs much introduction here. And there's this nice quote that in essence states that whenever a situation is reached which we don't know what to do, we make a random choice, try something if you want, and then we see what happens. And when something negative happens, we forget about what we did. And if something positive happens, we do it again. Now, this you could put into connection with Pavlov quite easily. Maybe this is also what you decided on would be the best strategy to go forward in the tasks you've just seen. And that's one of the reasons to make it probabilistic, so that this kind of reasoning doesn't apply so easily to it. However, this goes back to Alan Turing, 1948, which I particularly like since we've just heard in the previous talk that the roots of AI research is traced back to the mid-1950s. So we can again see that Alan Turing was a bit ahead of his time, even in that area as well. Now, if we take this principle, add on a couple of decades of research, we end up here, and that is again something that we've just heard being mentioned. In 2016, a computer program was written, AlphaGo, that was able to beat the human world champion in the game of Go. Why is that so interesting? It is the one game that always was believed wasn't able to be played by a computer successfully because of the combinatorial difficulties involved in this. And yet we managed to do so. Superficially, the media could claim again that the AI has beaten the human, is more intelligent than the human. And for the one game, that is definitely true, and for many, many other games by now as well. In general, as we've just heard so well, this is not the case. The research field I'm talking about is reinforcement learning. It's one area of machine learning. If you've seen the keynote just before, we've seen within machine learning there are neural networks, and a different aspect is reinforcement learning. And here we have another nice connection going back to Pavlov, because the term reinforcement learning appeared for the first time in English language in the translation of Pavlov's work. So how does it work? We have an agent and an environment. Basically, environment would be, for example, the study we present here, and the agent is the participant. Or, as for the example I've chosen here, the agent could be a player in a board game like chess, and the environment would be all the rules of the game being played. And the important point for reinforcement learning here is the fact that these two are very, very distinct from each other, meaning the agent has no information about what's going on within the environment. So you have to imagine, if this program would start to learn chess, it would start doing so without any knowledge of the rules of the game involved. And this is also true for our study later on, so that might be quite interesting to keep in mind. So what happens is the environment reports its current state to the agent, for example, the current position on the board. The agent makes a decision based on this state of an action, like the next move. And then the environment does two things. It gives a short-term feedback signal to the agent, not unlike what we've seen in the study just now, which says basically correct or wrong, with the added problem that in cases like the game of chess here, we don't know whether a certain move was particularly good or not. If we would know, the game would be solved, and we wouldn't need to have a program trained to learn it. So what we do in this case instead is usually just give no real feedback, and only once the game is decided, say, well, this game was good or bad, i.e. you've won or you've lost. And then the environment updates itself internally, reports that back to the agent, and we reiterate this loop. And what the agent wants to do is total up this feedback it gets after every move, and at the end maximize the sum, if we look at it from a mathematical point of view. So what we want to do is behave optimally in the long-term perspective. And there we struggle with two phenomena. The first one is the problem of exploration and exploitation, or the trade-off between the two. Let me give you a very concrete example here. If you have some ideas about the rules of chess, you might be able to follow along. Otherwise, it really doesn't matter as much. Important is that we have one move in here that pretty much wins the game. We have 8 moves that pretty much lose the game. In both cases, almost immediately, some of them straight away. And then we have 9 moves, and I think I missed here one even, that don't change much, and the game will go on for potentially a very long time. Now, as you can see by the numbers here, if you have no idea how the game works, choosing the one correct move here can take quite a bit of random experimentation. Now, let's assume you've chosen one of the 9 mediocre moves that just keeps the game going. And the game runs on, and eventually you win. Now you come to the same situation again, which in and of itself is already quite unlikely in such a complex game. And there we come back to the idea of long run times and huge computational power. But let's assume we do. Now, do you pick the same move again, knowing that then afterwards you've won the game? Or do you look for a potentially different move that might be better? And this is, in a nutshell, the problem of exploration versus exploitation, which in all of these learning problems is inherent here. And I think the numbers here show that you need to do quite a lot of exploration, exploration to eventually reach an optimal solution that is perfect instead of just good. The other problem, quite deeply inherent in these problems is the temporal credit assignment problem. And that is the following. Let's assume this game proceeds for a few more moves, and the computer made the move it should and wins the game. You can still ask which one of those two moves was the one that led to this good result. Now, in this case, it might be rather obvious that you need both of them. Now, if you would have made a different move, and the game would have gone on for a bit, and then we made some silly move and lost the game, again, the question remains, which of these moves actually got us to this bad outcome? And these two issues, meaning deciding between exploring different things that we know might not work out, and figuring out which one of the many steps that led to the conclusion, are the two inherent problems in reinforcement learning. Now, the issue was that we figured out in our collaboration in trying to compare computer learning versus humanoid learning, that these two issues need to be somewhat present in the task, and yet it needed to be simple enough to be also interesting for the to analyze the human learning, which is usually done on fairly simple problems. Now, no research really exists in the middle of nothing and comes out of nowhere. So the kind of tasks that we use as a blueprint have been analyzed before. Now, I'm not going to go into a lot of detail on the literature here because we don't have that much time. And the nice thing about the recording is if you're interested in the background here, you can always go back to the recording and just have a look at the papers. I just wanted to give the credit where it's due and say that there has been research before on using such sequential tasks to analyze learning. And even here, even though it's psychological research, the term reinforcement learning is being used, which again highlights some of the interdependencies between these lines of research. Another point, as I mentioned before, we wanted to compare human and artificial learning, is that there are several levels we can do this on. And one of the ones we looked at is confidence, particularly in such a probabilistic task where we're never quite sure whether we picked the right answer. Confidence can be quite interesting. On a different level, it then is interesting when we compare the senses to look at confidence we achieve through different senses. I hope you might have experienced this at the very beginning when you compared the visual and the auditory experience. And you might have noticed that for some of the visual ones, it was much harder to notice whether you've seen it twice or not. While for some of the more distinct auditory ones, it was quite a bit easier. So confidence can be a quite important thing, and there has been some study on this. And finally, the comparison across the senses on the human part. Again, very, very interesting to acknowledge that computers learn based on these states that are being reported, and these states might just be numbered. So if you have a small enough number of states, the computer just receives a number between 1 and, say, 6. While we perceive different situations with different senses and learn based on them. And in this study, we try to isolate at least 2 of them and compare what happens there. Now, I have to mention here that the original plan was not to go with visual and auditory learning, but with haptic learning as a comparison to visual learning. The issue was COVID that made at the time experimentation in the lab unfortunately impossible. We had to move things online. And so we ended up comparing visual and auditory senses. So that's why I listed here also research on tactile learning as well. So having a look at the time, let me tell you quickly what we actually had the participants and the computer go through. We had 3 pair of stimuli. Let's call them A, B, C, D, and E, F. I'll show you later some more examples of these. And always 2 were presented to the participant. Now, we could have presented the visual ones side by side. However, we wanted to keep the comparison to the auditory study as close as possible. And since we can't play the 2 sounds simultaneously and had to play them one after the other, we did the very same thing with the visual input as well. And as I mentioned before, there is no true answer which one is better than the other, but it's probabilistic. And you can see here the probabilities. We have this A-B pairing, in which A is 80% of the time correct. So A is almost always correct, and this should be fairly easy to pick up on. Now, if you look at EF, there we have the split of 60 to 40, which is much closer to 50-50 and will be much harder to see. And then with the CD pairing, which is in between, with 70 to 30, and later on in the results, we see that some quite interesting things happen with this CD pairing in here that we might not quite expect. So what did we do? We presented 20 versions of each pairing to the participant in a pseudo-randomized order, and then checked how good the participant got at picking the right answer. And then we rated this up to 6 times, only showing the pairs that they hadn't learned yet. Now, the advantage of this is that we can measure quite well how quickly participants and the computer learn by keeping track of how often we have to show them this block of 60 trials, or up to 60 trials at least. Also, we reflected the difference in difficulty in the accuracy we measured. As you can see, for the AB pairing, you had to get at least 65% correct to be considered having learned it. And for the EF pairing, we went down to being a bit better than guessing, in essence. Now, after they've learned this, they went into the evaluation period where we tested 3 things. We tested how well they've learned the known pairs, so A, B, C, D, and EF. And then we looked at whether they went beyond this. Now, having experienced the AB pairing a lot and how clear the decision was there, we then showed them A and B paired up with all the other ones. So A compared with CDEF and B compared with CDEF. The idea being that A is always correct and B is always wrong. So on top of learning the exact pairings, participants needed or were hoped to learn some kind of hierarchy between the 6 stimuli. And just to give you another example, now all side by side, this is basically the collection of potential stimuli we had for the visual task. Given that I can't show all the auditory ones on the same slide, I decided to not do that. That would take too much time. But just to compare, we had, for example, if you compare those 4 here, you can see we had waving clockwise or anti-clockwise with either the right or left hand, which are all kind of similar in motion. Others were maybe a little bit more distinct. So what were our assumptions going in, both in comparing the human learning and the artificial learning? And by the way, in case you're interested in that, for the artificial learning, we used a Q-learning approach, which is a very, very well-established and fundamental approach in reinforcement learning, which is suitable for smaller tasks. So we assumed from the beginning the computer would need more training iterations, which is almost always the case in pretty much everything we know. And this was indeed the case. We also assumed that the computer would eventually achieve high accuracy because the whole setting of probabilistic tasks is not that easy for us to learn. And if we look at the results here, we can see with a small exception at the AC pairing, and well, this might not be even significant here in the BD pairing, overall, the computer did better. We can also see, and this is quite interesting here, that the rough pattern of accuracy was quite similar. We have the same kind of dips and with the same kind of higher plateaus in the computer and the human learning. Finally, we would have assumed that human confidence would decrease with increasing difficulty. That was actually not quite the case. And this is now averaged across the different senses. We measured confidence in response time, saying that if you're not sure what you're doing, you need longer to decide what you want. And here we can see, and this is what I mentioned earlier, that the CD pairing, even though it's not the hardest one, took the longest time. And this is a point, again, I will come back at the very end of this, because we do have a theory what might be behind this. So this turned out actually to not be the case. And we also assumed that the computer's confidence would vary between different pairs, given that, strictly speaking, it should. The computer or everyone should be more certain in the AB comparison than on the EF comparison. And the CD comparison should be in between. And we found out this is actually not quite the case. Now, I don't have the time to go into the technical details of this, But we basically, Q tables is the knowledge representation within the algorithm. And based on these values, we can somehow derive how confident the computer is of making one decision over another one. And we can see here that for A, B, and C, D, it's pretty much the same. And even though the gap to EF looks big, if you look at the scale, it's just from 80 down to 78. It's not that big. So actually, the computer was pretty certain or equally sure across all the different pairs. Now, as for the inner human comparison, so to speak, between sight and hearing, which we could use the computer as a baseline for, the first thing we thought there would be a difference between them in speed. And if you look at this, at first sight, it looks like that learning speed in terms of number of blocks required is different, but it turns out this difference is not significant. So actually, they needed about the same number of blocks for learning the task by sight or by hearing. Now, if you look into accuracy, we can again see that CD kind of falls out of this, at least in the audio case. We can also see that it slightly falls off with difficulty in the vision case, which is exactly what we would have expected overall. And we can see that this dip we've seen earlier is actually due to the audio channel. But, so we see in the CD case, there's a significant difference in accuracy. If we average them out, though, across all the pairs, we can again find that this accuracy stops being significant, the difference in here. And finally, the confidence. And this is quite interesting, given what we've just seen about the accuracy. We can see that the answer in the audio case was much faster than in the visual case, with the exception of this. If we look at the CD pairing again, we can see that here in the vision case, the answer took longer in this CD pairing. So we see that this falls always out of what we would expect. And as I said, I'll get to this in just a second. While if we compare familiar to new pairings, we can see the increase in response time we would expect with a lack of confidence, which in some sense also validates that we approximate confidence with this response time measurement. So this is indeed different. Now, unfortunately, I'm running out of time here. So let me quickly emphasize one thing. Well, first of all, we're playing with the idea of adding senses to the artificial agent. We've just heard that artificial intelligence algorithms or techniques are quite good when it comes to visual tasks or sometimes even text-based tasks or audio tasks. So we could add these on top of the existing algorithm to give the agent a sense of senses and get a more finer comparison between the two. We also want to include more humanoid senses as well. At latest, when we come back to the lab again, this is going to be added in. And finally, the randomized stimuli is what I've been hinting at the entire time, because our theory is that this CD comparison that turned out to be so different than we expected comes down to an unfortunate choice of the two stimuli that might have been very difficult to distinguish, because what we didn't do is randomize the stimuli that we selected for the different letters. And with this, we hope to get closer to understanding how the different types of learning compare, which can have benefits in both directions. It can both inspire us when we're looking for new and different algorithms in the machine learning context, as well as start to build bridges between human and machine corporations when we get to that. And with that, I thank you for your attention, and I'm happy to answer questions that are coming up. And as far as I know, Merle tried to join us as well, if possible, for this.
Thank you, Maximilian, first of all, for that great talk. I think it's very interesting to compare the different learning, with confidence, and like the way you showed it was quite interesting. I would just pass on to you with a question that appeared in the chat. So someone asked, once an AI system learns to play a game well, can we learn from it in some meaningful, smart tactics to play the game better ourselves?
This is in fact what happened in a large variety of games. So the first game that caught a lot of attention when it was solved with basically reinforcement learning, and which led to a massive increase in interest in the research in reinforcement learning was in 1995, backgammon actually. And it's quite interesting because backgammon is a random game. You're throwing dice in the game. And I, at the time, wasn't aware actually that there is literature on how to play backgammon well. There is. And it turns out that watching the computer play backgammon, again, be on a human worldwide level, that a lot of typical strategies were rewritten. Books were basically falsified and rethought and rewritten because the computer found ways to play this that were not thought of before. And if we now look into more recent times, Go and chess, also there, the way the computer is playing has impact. So, for example, the computer is quite often used as ground truth, more or less, to assess certain situations and to basically know what should be the correct answer, or at least how good the two players are in comparison to each other. And for example, in Go, there's this nice quote that the player at the time who played the computer in 2016 said that the computer does not play human-like. But that he could, in essence, it would have failed the Turing test in this case, if you go back to that, because the player could tell from the playing style that there was not a human playing. But yes, we can learn a lot in these games. The difficulty is now making the transition to something more significant than games.
Thank you so much. I think there is one other question in the chat, but Merle already tried to answer it. Maybe you can add something as well. But I already see our next speaker, Emily Cross, in the line. Thank you, Maximilian, again for taking the time for that fascinating talk. And happy to see you later in one of the social interaction meetings we have.
Yes,
thank you. See you later. And with that, I'm going to introduce our next speaker, Professor Emily Cross. She's a professor of social robotics and a co-director of the Social Brain and Action Lab, as well as a PI on the ERC project Social Robotics. And she's located at the University of Glasgow. Generally, she works on complex action learning and perception with a wide range of different tools, from neuroimaging to behavioral techniques. Today, she will will take on an abstract perspective and reflect on what cognitive and brain sciences can contribute to our understanding of social robots. Emily, you can turn on your video and audio. We are very happy to have you here. Welcome. Great that you can join us. You can try to share your screen as well so that we can see your slides.
Doing that right now, and oops.
I will give you, as usual, the 5-minute warning, kind of when the end approaches, and then we can do a couple of questions, just as we did with Maximilian in the end.
That's perfect.
Yeah, we can see your slides. That looks perfect to me. So please, Emily, take it away.
Wonderful. Well, thank you so much for the introduction, and thank you so much as well for the invitation to Merrill for organizing, and colleagues, this fantastic workshop. I can't tell you what a pleasure it is to be here, the bottom of the world, taking part in this very international, dynamic, and just worldwide meeting that's bringing together so many interesting minds and thinkers and perspectives. So yeah, it's, as I said in my tweet earlier today, it's like being in a candy shop with all of your favorite thinkers and ideas. So I just feel really delighted to be part of this. So thank you. My talk today will be kind of in two parts, not exactly of equal portions. I'm going to talk a little bit about a theoretical piece that I published recently, kind of talking about what we as cognitive and brain scientists, which is what I am, might be able to contribute to this endeavor of understanding how humans and machines, and in particular humans and robots, might work together harmoniously in the future. And then I'll talk just a little bit of a whistle-stop tour about some of the research that's going on in my lab, but you'll have heard about some of that yesterday from Maki Ruxby, and you'll be hearing some other fantastic lab-affiliated folks today with Nate Caruana and Ruud Hortensius. So we have a lot of kind of lab love spread throughout this conference. So I'll leave a lot of the really exciting stuff to them to tell you about. So I'd like to begin by placing this research and kind of my interest in it in a little bit of a broader context. So as we've been hearing about pretty much since the start of this workshop, there's lots of interest and excitement for what the future for artificial intelligence holds. And one aspect that is really capturing people's imagination and attention, perhaps more than any other, is the widespread introduction of artificially intelligent superhuman robots, the likes of which we've all come to know and love and or fear from films, books, and TV shows, some of the examples that you see here. So while we're all sober enough in this workshop to appreciate that we're really far off from any sort of superhuman machine like we see Hollywood depicting, and I think Michael Winikoff gave us a really good indication of that in his keynote this morning, that's not happening anytime soon, there are still a number of different robots that are making inroads into our social spheres and social spaces and into kind of really close and intimate human interactions, and kind of understanding better how people might be able to work with these robots and kind of what's going on, what the neurocognitive mechanisms and consequences are when we do introduce and interface with these intelligent machines in these social spaces, what those consequences are going to be. So, there's been a proliferation of machines and other sorts of artificial agents that are designed ever more intelligently to engage people on a social level. But our understanding of how, what's actually going on psychologically and cognitively and neuroscientifically in the human brain, this remains really, really rudimentary. There's this kind of heuristic, this rough idea that, well, we know more and more over the past 20 years or so about social cognition and social neuroscience and what's going on in the human brain when we're interacting with other people, though our understanding of that is still very, very basic. So there's this kind of heuristic that, well, maybe we're using kind of the same mechanisms, the same sort of machinery to make sense of robots and other artificially intelligent social agents that we encounter. So there's this kind of, well, maybe they're kind of similar-ish. And what I would like to argue in the first part of this talk today, and what we talk about in this recently published TICS paper, is that it's probably going to be a lot more complicated than just using human social cognition as your kind of rough heuristic for understanding what's going on when we're perceiving and interacting with especially physically embodied robots. There's a number of other things that I'll touch on that I think is going to be really important, I think are going to be really important for us to consider and to study deeply as well. So hopefully this endeavor of how we perceive and interact with artificially intelligent social machines can very much be aided by the cognitive and brain sciences. But you might be sitting back and saying, well, why should we actually care about, what's going on in the human side of human robot interaction? Well, I would argue there's two really good reasons why we should care about this. One is that if we can understand what's going on in the human brain and cognition and behavior when we're trying to engage in a meaningful way with social robots, this should help us to improve the design and programming and make these agents ever more socially engaging and collaborative. And that, of course, is precisely what we want them to do in order to help us in social roles. So that's one piece. But the other piece that is very much of interest to people working on the human sciences and the cognition and neuroscience side of things is that a better understanding of the flexibility and limits of human neurocognition when we're engaging with people or artificial agents should help us to understand the human brain and kind of its basic mechanisms in a much better way. So I would say there's just kind of two complementary, both really important reasons why we should care about the human side of human-robot interaction more. So thinking about how to best position this research within this fledgling field, we have social cognition, which has so far been kind of the wedge that a lot of this research has focused on. So lots of comparisons between people and robots. What happens when you look at people, when you interact with people compared to when you interact with robots? And that's great. It's given us a really good start. But I'm going to argue that if we kind of widen our perspective or our lens or some of the factors that are going to be really important to also consider in this endeavor, we're going to come up with a much better and a much more complete understanding. So one of those things that we're going to have to really think about carefully and often gets kind of swept under the table between studies and when people kind of pluck a human robot interaction study to kind of support their psychological claim are all of the complexities that come with machine variation and how there's no not that any two humans are created equal, but any two machines are definitely not created equal, and that isn't really taken into account as much as it should be. Also, I'm going to argue for broadening the perspective beyond social cognition to be thinking about what we can learn and what we can gain from considering diverse brain systems. And finally, I would argue, and I will argue, that there's some particularly unique challenges, especially for those in social cognition and social neuroscience coming to the table to take part in this research endeavor that we're going to have to carefully think about how to take into account. So the first pillar of this framework that we propose in this paper is this idea of respecting the important and distinct roles played by machine variation. And there's just a few kind of sketches of what those types of machine variation are in that box there, but let me sketch this out for you in a slightly different way. So we're thinking about machine variety. And when we think about machine variety, let's start with people, which are very much not machines, but we have a lot of experience with people, and we kind of know that each of the three individuals we see pictured here, those are people. There's no question about that. And yeah, they're famous people. We might be familiar with kind of other information about them, but those are people. But then we can start to think about how we might think about and embed our knowledge of machines and socially intelligent machines. So we can think about objects, and objects are very distinct from people, and that's very clear. There's a lot of kind of space in between them. But then we can drill down into objects like in an ever more specific way. So we can think about a type of objects that we kind of interact with to achieve certain goals, which are tools. We can think about even more sophisticated tools, which are machines, which we can achieve all manner of even more complex and sophisticated goals with. And then over the past 20 or 30 years, we've had the advent of artificially intelligent machines that might not look like much on the surface, but can achieve all manner of even more sophisticated tasks. And then kind of drilling down and bringing us, as you can see, ever closer perhaps to humans, we have artificially intelligent social machines. So these aren't just machines imbued with artificial intelligence, but these are machines that are specifically designed to engage with us on a social level. And we can see there's a lot of variety within that object category right there, especially as we get down to these artificially intelligent social machines. But I'm going to argue that maybe we should not just be thinking about these really strict categorical axes or categorical differentiations that we see here, but we can instead think about different dimensions or features of objects. And this might bring us much closer to kind of understanding what's going to matter when we're interacting with or perceiving a robot, for example. So some of the dimensions or features of objects that might be really important depending on the task at hand include your prior experience or expectations, their functional repertoire, form to function mapping, how big they are, how social they are, how intelligent they are. Do they have a human-like form or a very unhuman-like form? And if we kind of take this more kind of feature mapping approach, we can start to kind of say, okay, well, different objects as we go through the object space here will have really different properties and dimensions based on what their design is and what their intended use is. So we can also see here that objects that might be in the same category in the left-hand column have really different features. So it could possibly be quite a fruitless task to focus on categorical distinctions. And instead, maybe when we think about machine variety, we can think more about different dimensions rather than just categories. So that's kind of one challenge, and it's not easy to kind of take into account, but I think it's something that we should be thinking about rather than just that's a robot, that's a human, or that's a tool, that's a robot, that's a human. The second pillar of this framework is speaking to the proposal or the strong urging to take into account not just social cognition, but diverse and interacting cognitive and brain systems that will be required to support successful human-robot interaction. So you can see a few here. We have object, tool, social cognition, semantics, attention, memory, and of course, social is just one small piece of that. But so far, there's been nearly an exclusive focus on how people perceive and interact with robots versus humans. And this is going to run a real risk of overemphasizing the human-like or social qualities of a robot and how important those are for human-machine interactions, when indeed it could be many other features that are more important. And it's not just the kind of human-like socialness that's most important. And in another paper that you might hear more about later today, I'm not sure if Ruud will be talking about this, but in this review paper that Ruud, Anna, and I from the lab wrote last year, we kind of talk about the importance of object-specific brain regions and what's going on when we're interacting and perceiving robots in these object representative brain regions, and how these are going to be really important as well. So it's not just human-based social cognition. What are parts, what's FFA, what's EBA, what are these STS type regions doing? But let's think about object categorization and cognition and the neural substrates of this as well. So yeah, moving beyond social cognition is going to be important. And the third and final pillar of this new framework is one that I think is really exciting, but is perhaps the most challenging. And this concerns the unique challenges and opportunities that studying human-robot interactions or kind of people's engagement with social robots might present. So we have a bunch of different challenges that are listed in this blue box here, but I'll just highlight a few of them and why they're particularly, going to be something that is going to take our field a lot of time to really kind of come to terms with and make sense of. So the first is novelty and lack of experience. People just don't have a lot of experience or know what to expect with when they see a robot kind of plopped on the table in front of them. That's a really good and interesting thing, but it also means that everyone's going to be coming with different expectations. Another really interesting fact that again, just doesn't get spoken about all that much, especially when people from psychology and cognition start to look at human-robot interaction research, is the whole thing with the Wizard of Oz setup. So almost, not every, but I think there was a statistic that was just published that roughly 80% of human-robot interaction studies, and indeed a lot of these that are in psychology, there's an experimenter pulling the strings behind the scenes. So the robot is not behaving autonomously. And if we're trying to understand how people are going to engage with and build relationships with and cooperate with autonomous artificial agents, we cannot be using Wizard of Oz the whole time. And we have to be really clear that understanding that there's a person essentially treating a robot as a puppet, this is really different than having autonomous robots. And this kind of, these are all variations perhaps on the same theme, but people have really skewed or vague expectations, which kind of comes back to this first thing about novelty and lack of experience. But the more and more we see these beautiful images that, just are all over Google about robots, beautiful robots doing really clever and sophisticated human-like behaviors, then people start to have expectations that this should be what robots might be able to do. And there's a lot of really good research the world over that's kind of looking at this mismatch between expectations and reality, but that work needs to continue, and we need to kind of take that understanding into all of our work in this domain. And, again, coming back to Michael Winikoff's warning this morning about media influences. So he was talking about really knowing the expertise level of someone who has a breathless proclamation about, what AI is going to do and how it's going to destroy your life. Well, I think we also have to think about media influences with human-robot interaction, because we have seen so much throughout the years and throughout our Netflix scrolling of robots doing all manner of things that we're just not going to see them do anytime soon. And just kind of understanding whether people are sci-fi buffs, whether they've kind of seen lots of Pixar movies, or they, kind of were frightened of Terminator as a kid. All of these things are going to really shape interactions with and perceptions of robots in ways that I would argue we don't see this as kind of importantly and as widespread in other areas of cognition, of human cognition. So to sum up kind of the points of what we're proposing in this paper, what I'm trying to suggest as for a new field of social robotics and kind of human cognition meets social robotics, it's far more complex than just social cognition with robots. What we're trying to put forth in this paper is a way that we can frame or approach this complexity. And this proposed framework is really trying to harness key insights from cognitive neuroscience, not just social cognition, to address the novel and really unusual demands posed by human interactions with social machines. And as I say here, true progress in developing machines that engage us on a social level will really only come with interdisciplinary collaboration across the social, life, and computing sciences. And I think the socialBRIDGES workshop is really trying to build some of those bridges nicely. And I would like to say that cognitive and social neuroscience have a lot more to offer social robotics than just social neurocognition with robots. We can do better, we must do better, and we will do better. And what we lay out in this paper is just one way to approach the complexity of the task at hand. So that's kind of the bulk of the talk. Now I'm going to give you just a sneak peek, because we have, I think, about 3 to 7 more minutes here to talk about some of the work that's emerging from our lab. And I should say that this theoretical piece is a new piece, and everything that I'm going to show you here hasn't followed those kind of lofty ideals yet, but it's kind of a way that I want to think about framing research within the lab going into the future. But there's still a lot of low-hanging fruit to be done using, depending on what your question is, social cognition comparisons. So we have a wonderful cast of characters that's in our lab right now, actually across our labs at Glasgow and here in Sydney at Macquarie University. And we're really interested in kind of asking questions about social cognition as they relates to social robots into the future. But again, when I say social cognition, I don't mean just sticking with that, but kind of taking this broader perspective, this bigger, wider lens for that. So one question that we might ask is, how can we examine social specificity versus domain general neuroprocessing and behavioral strategies when we engage or socially engage with robots? This is a really nice paper with Rude that came out a few years ago, where we're trying to kind of map some of the neural areas that are probably going to be key targets and really relevant as we kind of take further steps towards this endeavor. And just a real quick kind of overview of some of the latest findings and questions that we're asking and trying to answer in the lab. We've been doing some work with synchrony and social reward and trying to understand the extent to which synchronizing with a robot makes you feel more amiable towards them. And the kind of spoiler alert here is that it's not a very robust finding, but the beauty of pre-registered research and kind of staying what our hypotheses are and what we're basing them on means that hopefully that we won't have the file drawer problem, and you'll just see all the positive results published, but you'll also see some of these really robustly supported null effects. We're also looking at some interesting questions with prisoner dilemma games and other economic games with robots, and the extent to which people show social reciprocity when they're competing against robots. And some even more recent work with T.E. C, who's the first author on that, is looking at the impact of emotion, of robots' displays of emotion on cooperation. Also, the extent to which we perceive robots as social agents and how social perception might kind of interfere with other sorts of cognitive processing in the human brain. Some nice work by Anna Henschel and colleagues that just came out this year in Collabora, and some really cool stuff with a collaboration across London and Edinburgh and Glasgow and Macquarie, looking at kind of linguistic framings of robots and different races of social interactions. And that's such a cool study, and I can't wait to tell you more about it as data come in. Some really nice work as well with the PhD student Guy Laban, looking at emotional disclosure to robots and the extent to which robots might be a useful tool for kind of having people talk about concerns, problems, etc. And again, lots of really exciting things happening in that space, having to do with COVID as well right now. And that's something I'll tell you just a little tiny bit about here, is the extent to which you might be able to build more empathy for pain expressed by a robot after long-term social engagement. So I know we only have just a few minutes left. I'll just tell you a few things about this study, because it was, I think, an interesting study. We nicely pre-registered it and had some clear ideas for what we expected to find. But as always, in real life research, the findings are not quite what we expected. So our question here was, to what extent can, if people spend a lot of time interacting with this really cute little palm-sized robot Cosmo, which some of you might be familiar with, if people take that robot home for a week and really kind of play lots of games with it, to what extent will you start to feel more empathically towards that robot when it looks like it's in pain? With this kind of like pretend electric shock therapy. So what you can see here is just a video, and there's sound, but you can't hear it. But what participants were seeing here was a little video of the robot with a circuit board behind it. And when the red light went on, the robot was supposed to be shocked, and the robot would either have kind of like really kind of uncomfortable shocking and have these painful expressions and vocalizations, or we'd say that there could be kind of a nice stimulating massage shock paradigm, and the robot would look very happy. And we also had those exact same conditions emulated with a human actor. And again, no robots or humans were actually harmed during the making of these videos. And what we did was we sent participants home then with the robot in between kind of identical fMRI sessions where we scanned their brains while they watched these different videos of the humans and the robots kind of in pleasure or pain. And we asked people to spend at least a half hour a day kind of getting to know the robot, playing games with it, socializing with it, etc. And gave them lots of instructions about how to do that. Our participants really enjoyed the task. They gave us all sorts of wonderful photographs of them getting to know their cosmos at home. And I think quite a few pets were made jealous. But just to show you one of the many findings from this study, we functionally localized brain circuits that we know to be involved in empathy by using this partly cloudy functional localizer task from Rebecca Sachs's lab in the States. And what we were really interested in was the extent to which, after participants spend this week interacting with the robot, do we start to see that there's kind of more engagement of kind of human robot overlapping within these empathy related brain regions. Well, these are regions for pain, empathy in the human brain. And it's a little hard to go through everything that's going on in this slide, but essentially what we wanted to see was these two traces on the plot here showing quite a lower position after the week of training. So kind of to be lower than the two gray dots. And as you can see, there's really no differences. So what we concluded from this study, and again, I'm not doing it justice, it's a long paper, please read it if you're interested, but we found no evidence for neural mechanisms associated with empathy towards people to really kind of show more overlap between humans and robots after you socialize with a robot. So there's kind of, these are quite distinct things, and we can't just kind of trick people or convince people that robots are kind of going to deserve empathy in the same way that humans do. That's just one study, that's just one robot, but it's kind of an exciting space. We have lots of other stuff going on, which I'm going to skip over because we're out of time. I'll just finish off with two quotes, one is that's by technology writer Eric Sofke, who says, "We're only barely scratching the surface of the brain's social algorithms, which become even more complicated and unpredictable when we interface with technology." I couldn't agree more. And another fantastic psychologist working at the intersection of robotics and brain sciences in Auckland, Elizabeth Broadbent, suggests that the further we go down the path towards making and interacting with artificial humans, the more truths we learn about ourselves. So I think just, again, a really nice interdisciplinary perspective. Do I have any fine thoughts to say? How will humans and AI interact in 5 years? I don't know, but I think that we're only going to be able to answer this question by bringing together people working in the mind sciences and brain sciences, cognition as well, to begin to get good answers to these questions. I think Maki had a slide up for this yesterday, but I would like to encourage anyone who's interested to come along to our virtual social interactions workshop, which is free, and it's going to be happening in June and July this year. Some fantastic keynotes, and we'd love to have any of you interested come along. And I'll finally be quiet and I'll thank my team members and funders, and I'm happy to take any questions. Thank you.
Thanks so much, Emily. That was a wonderful talk. I learned a lot on kind of the interdisciplinary nature and the combination of neuroimaging with the social aspects. That was fascinating. Thank you so much for the talk, taking the time to give the talk. First of all, I just directly move to the questions because we have a couple. As we move away from AI tools to AI social agents, should we worry about humans exploiting AI agents in ways in which humans do not exploit humans?
Great question. And I think we absolutely should worry about that. And I think the wonderful thing is that there's lots of people who are working on this in this space. I think there's quite a few people in the Netherlands in particular that seems to be a hotbed for these sorts of questions and issues. Yeah, I think there's a lot of people who have their finger on the pulse of this, and this is where we're going to need even more interdisciplinary work from philosophers, from lawyers, from people who really kind of understand the ethics deeply. And yep, I think we should be concerned, but fortunately, people are kind of working on it now.
Yes. The next question, if robots look a lot like humans, will we start to treat them more like we treat other humans, or will we start to treat humans more like we treat machines?
Oh, no, that's a really cool question. So I think the first half of that question, if robots look more like humans, will we start to treat them more like humans? The evidence for that so far is mixed. And again, kind of coming back to that first pillar, talking about machine variation, it's really hard to kind of say, well, there's these 4 studies that have found this, therefore we can conclude that this is what happens. It's just every machine, every robot is different. But I don't think the evidence so far is compelling or clear that the more human-like a robot becomes, the more human-like people treat it. It's complicated. But this idea about kind of then treating humans to be more machine-like, this is another really interesting question, but we also need philosophers and ethicists and people who really can get at these questions in subtle and nuanced ways, because I don't think we know the answer to that yet. But again, I think it's something we probably should be concerned about and at least, keeping our eye on.
Yeah, something to be wary of at least, right? Yeah. I would agree with that. The last question: when do people cooperate, and when don't they? When they interact with robots in social dilemmas? You mentioned the prisoner dilemma.
Yeah. So this is, again, an emerging space. There's not a ton of work, but in our particular task with our particular robot, I know it sounds really boring to keep saying that, but I think it's important because we can't say like, oh, well, we found that people do this with robots. But with our task, with our robot, we find that people really use much more of a tit for tat strategy with robots than they do with humans. So if the robot cooperates, they cooperate. If the robot competes, they compete. And we really see this kind of, not so much an escalation, but just a tit for tat strategy for the prisoner's dilemma games that we found with our people and our robots. So again, like, these questions are really of interest to lots of people designing kind of co-working robots, especially working with people on factory floors or even kind of in more decision-making type tasks. So I think this is a very open area, and I'd like to encourage people who are interested to please come and do more research in this domain because it's needed.
Yes, especially the cooperation part seems to be super relevant and interesting. Like, you can implement very, basic cooperation tasks, like in the factories where you have these tasks and they need to do some communication, and then you could do even far-fetched ideas. Like probably the closest way would be what Gordon Shang presented yesterday at his talk, where he showed artificial skin, where there's kind of the next robot style, which is more sensory involved in the environment. But with that, we have to leave it there. Emily, thank you so much again for taking the time and for that great talk. And look forward to the future state and the future presentation we have later from your lab as well. And if you can post the link maybe in the chat or somewhere on the whiteboard, some sphere that people can access it, I think that would be great.
Will do.
And then with that, I see already the next speaker in line. Thank you again so much, and see you. And with that, we're already moving to the last speaker before our lunch break, which we think we well deserved. I warmly welcome Nathan Kuana. He is a research fellow and lecturer at Macquarie University in Australia. I hope I pronounced that not horribly wrong. He works on understanding social attention and coordination, which is called joint attention and might be familiar to some. Today, he will take us behind the virtual curtain and show us how social interaction and information processing operates in virtual reality. And with that, Nathan, we're happy to have you. If you can share your slides, then people can enjoy your presentation. That looks excellent. Wonderful.
Great, thank you so much.
When you're ready, you can go.
Great, thank you. And it's great to be a part of Social Bridges and what has been a really interesting and engaging series of talks so far. So I'll be taking a slightly inverse approach today to talk about how we understand and relate to artificial agents, because in my work, I actually use artificial agents to as a tool to understand human social cognition and interaction, and the mechanisms that are engaged when we interact with artificial agents, as well as the psychological factors that influence the engagement of these mechanisms and that influence how we relate to other human agents. And so touching on some of the ideas presented by Antonia Hamilton yesterday and Emily Cross just now, I hope that this information will eventually inform how we can design and implement social behaviors in artificial agents and position them to maximize our ability to interact optimally with them in social contexts. And the context in which I do this research is joint attention, which I think is a really good paradigm for investigating reciprocal social interactions, but also social information processing. So joint attention is our ability to coordinate our attention with others and attend to the same thing. And this typically involves one person initiating a joint attention bid by looking at or gazing towards, or pointing towards or talking about an object. And then another person recognizing that behavior as meaningful and communicative and intentional, and also aligning their attention with their partner. And so joint attention is important because it allows us to share experiences with others, and it's through these shared experiences that we learn about others and how other minds work, but also how we learn through others experientially. And so language development, for example, is one type of social learning that we achieve through this experiential type of shared experiences with others. And so when we have difficulties achieving joint attention with other humans or other agents, these learning opportunities are mitigated. And this is often seen in autism, where joint attention difficulties lead to other social communication difficulties and developmental delays. Now, a problem with joint attention research and social interaction research more broadly is that the experimental paradigms that have been used to understand the mechanisms supporting these interactions have really failed on the whole to achieve a balance between ecological validity in capturing the full complexity of these interactive phenomena, but also achieving experimental control and objectivity in our measures of brain behavior, often favoring the latter over the former. And so Leo Schulbar and colleagues in 2013 argued that this has resulted in this dark matter of social cognition, and argued that we really need interactive paradigms to understand interactive phenomena. And these paradigms need to allow two people to really engage and interact with each other, where there's a reciprocal exchange of dynamic and complex social information. So inspired by some early approaches using interactive eye tracking tasks, I developed this interactive eye tracking task where participants interact with an on-screen avatar who they believe is being controlled by another person named Alan in a nearby eye tracking lab, but in reality is controlled by a gaze contingent algorithm that simulates a reciprocal exchange of eye movements. And together they play a game where they have to locate and catch a burglar hiding inside one of these 6 houses on the screen. Participants have to search the houses with the blue doors, and Alan has to search the houses with the brown doors. And so on some trials, participants will find the burglar, make eye contact with Alan and guide him to the correct location. On other trials, they won't find the burglar and have to wait for Alan to guide them to the correct location. They also complete non-social versions of the trials where they have to engage in the same sequence of eye movements, but they complete the responding and initiating trials on their own by looking back at this central fixation point and catching the burglar on their own, or following this arrow cue to the correct location. And we've implemented this paradigm in an fMRI study to look at the neural correlates of initiating and responding to joint attention bids, separating out the social and non-social aspects of these mechanisms, and looking at the overlap of these mechanisms. And in using similar paradigms in ERP studies, looking at the neural time course of evaluating joint attention experiences, which I'll come back to later on. Eye tracking studies as well, looking at how we differentiate communicative from non-communicative eye movements during joint attention, and how we pass and process spatial signals that can help us predict an upcoming joint attention bid from non-communicative eye movements. And finally, looking at how joint attention responsivity can differ in autistic adults and adolescents, as well as patients with schizophrenia. And so these interactive eye tracking paradigms, and also those by others, have allowed us to creep closer to this dark matter, but they're still really limited in that they are using these pre-programmed agents, which are not quite Wizard of Oz. They are pre-programmed, but lots of assumptions have been made in their development about the temporal and spatial dynamics of the nonverbal behaviors that they display. And so going back to Antonio's talk yesterday, these paradigms that we developed in some ways are cheating because we're skipping that human-human interaction exploration stage of this research. Another limitation of this work is that it's been restricted to, in the most part, to examining joint intention based on gaze-only communication. And that doesn't reflect how we do joint attention out in the wild. Now, there are a few reasons beyond the practical reasons for looking at eyes only as to why there has been this historical focus on examining eye gaze and social interaction, but in particular joint attention research. One reason I think is the autism phenotype. We know that autistic individuals often have difficulties looking at eyes and establishing eye contact with others. For many, this can be a distressing or even physically painful experience. And so it's often been assumed that these difficulties with looking at and processing gaze in autism are fundamentally consequential for other aspects of social cognition. And therefore, they must be important in neurotypical social cognition and interaction. And I think there are some flaws with that logic, which I think is to be discussed in another talk. But another reason is this cooperative eye hypothesis idea, which is the idea that human eye gaze is very physically salient and unique in that we have this high contrast between our sclera and iris that make our eye movements very salient to conspecifics. And this has potentially allowed us to collaborate with others in a pre-language era of our evolutionary history, but to also allow us to signal threat to conspecifics. And another idea is that eye gaze is unique or special because it serves a uniquely dual function in both signaling and perceiving social information during interactions. And so for this reason, it provides continuous and ubiquitous information about what someone is looking at and what they might be thinking and intending to do next. But I think this is an interesting argument to make because this very feature of eye gaze also makes it an inherently ambiguous and noisy signal for coordination because an eye movement on its own can mean a whole range of different things, and not all eye movements are meaningful and communicative. And so the reality is that we don't use eye gaze information in isolation, and sometimes we don't use it at all to coordinate with others. Not all our interactions are face-to-face, many are side-by-side. And that might in some small part, explain why we find this new normal face-to-face communications over Zoom so taxing and tiring. So you and Smith have recently argued that other types of nonverbal cues that we can use to achieve joint attention, like a situationally relevant hand gesture, a pointing gesture, whilst it might be less ubiquitous and slower to execute than a gaze shift, it can be more spatially precise, less ambiguous in conveying intent, and also require less social cognitive processing to extract the relevant spatial information to guide our responses to joint attention bids. And so in a related study, they found that in infant parent dyads, infants actually allocated very little attention to their parent's face during joint attention and during joint play. And so perhaps eye gaze is actually not so important in coordinating with others, at least in early development. But this is tricky because the parents were triadically attending to the face and hand object dynamics. So it's unclear to what extent interacting adults integrate and allocate attention across multiple nonverbal cues to coordinate and align with other agents. So to address this question, we had 21 dyads come into the lab and we immersed them in virtual reality using head-mounted displays that had integrated Tobii eye trackers inside them. And we also tracked their hand pointing movements with a motion tracker sensor on their index finger. And we immersed them in a virtual reality environment that where they were able to naturally move their eyes, their heads, and their hands as they played a joint attention task with their partner. And so they had to initiate and respond to joint attention bids using a hand pointing gesture in this task, but there was no explicit mention made of eye gaze at all. And so in this task, on each trial, participants would see 3 numbers presented on these cubes in front of them. They could only see their side of the cube. And so if they saw 3 even numbers, so a 2, a 4, and a 6, they had to initiate joint attention to the highest value number, so the 6. But if they saw three odd numbers or a mixture of even and odd numbers, they had to wait for their partner to initiate joint attention and respond by also pointing to the correct location. And so this created a task context in which participants had to shift their gaze around the social environment to identify the target of joint attention, but to also determine their social role as the initiator or the responder. And there was an equal division, I should say, of trials in which people were the initiator or the responder. And so I'll show you a very short video of what one trial looked like. So here you can see the initiator points to initiate and the responder points to respond. Very simple and very quick. I'll play that one more time. And so one of our first questions were in this study, in this context where participants are explicitly initiating joint attention with a hand pointing gesture, which is very spatially precise, are they actually conveying any useful gaze information that can also support coordination? And what we expected to find was that initiators would predictively and congruently fixate the target before pointing to the target. And although this was true on some trials, there were also trials where this wasn't the case. So on this particular trial, what you'll see is the initiator actually finds a number 6 straight away, but then has to search the other 2 locations to make sure that they are also even numbers. And then she initiates joint attention without predictively gazing towards that location. So she's displaying incongruent gaze point behavior. And so her eye movements here, her gaze shifts are not predictive or useful in facilitating joint attention responsivity. So we actually found that this initiator gaze congruency behavior was highly variable across participants. It was congruent on about half the trials, but as you can see here, some initiators were quite reliably predictive in their gaze behaviors before initiating joint attention, but some initiators were reliably unpredictive in their gaze movements in the lead up to a joint attention episode. We also wanted to see whether responders of joint attention were actually attending to their partner's face to extract gaze information during joint attention. And this was measured as an overt fixation on their partner's face, the initiator's face, during the joint attention episode. And again, we found that this behavior was also highly variable across participants. You can see here that it happened on average about 60% of the time, but there's also some participants here who were reliable face lookers during joint attention, and others who very rarely looked at their partner's face during joint attention. But the critical question that we wanted to ask was whether responders are actually integrating and using gaze information to facilitate their responsivity to the point-cued joint attention bids. And we measured this as saccadic reaction times to the pointing gesture. And we analyzed these data using linear mixed effects models, including subject, pair, and trial as random effects. And we found that participants were significantly faster to respond to point-cued joint attention bids when the point was preceded by a gaze shift that predictably cued or was congruent with the target location. This was true when we modeled all of the trials, and also when we separately modeled the trials where participants overtly attended to their partner's face, but it wasn't significant when participants didn't overtly attend to their partner's face. And so it suggests that this gaze integration does require, at least in this context, overt attention to the agent's face. So what we find here is that even though we're not relying explicitly on the use of gaze, either as an initiator or as a strategy as an initiator or a responder during joint attention, we do convey useful gaze information, we do attend to this information, and we do integrate this information to guide our responses. But this does vary in the extent to which we do this across individuals. And so I think an important future avenue for research looking at how we interact with other agents, whether they be human or artificial agents, avatars or robots, is to look at all the many factors that influence how we engage in these different implicit or explicit social information processing strategies with others. And some of these factors include contextual factors, like what type of interaction are we engaged in, how many potential targets are there, are they dynamic, and what types of different behaviors are we integrating when we collaborate and interact with other people. Also, how similar the dyad are to each other and how similar they perceive each other to be and how familiar they are with each other. And psychological factors like mood and personality. So if you are an introverted person or a socially anxious person, are you going to attend to gaze information less and use that strategy less? And finally, what we're looking at the moment are how differences in initiator behavior changes our strategies for social information processing. And some of the factors that we're looking at are differences in the salience of gaze shifts, so how much head movements are involved, but also whether we use gaze information strategies more if we're interacting with an agent who reliably provides us with useful gaze information. And so ways in which we're asking these and answering these questions is by using variations of this paradigm, where we also have participants come into the lab and interact with an agent, with a confederate who we train and cue to behave in a certain way. So offering some more experimental control by sort of programming a human in real time. But also moving back to these artificial agents where people come into the lab and they think they're interacting with their human partner, but they're both interacting with an artificial agent that we program and manipulate aspects like salience and gaze reliability. The difference here with our previous work, however, is that we are using genuine human behavior to drive the temporal dynamics of gaze and hand movement behavior. So this provides a nice segue to the second part of my talk, where I'll be talking about whether it really matters if people believe that they're interacting with an intentional and sentient human agent or a computer that isn't sentient in these artificial interactions. And this question initially emerged for me as a methodological question because I initially assumed in my early work that it was an important ingredient in ecological validity for participants to believe that they're interacting with a human. But I wondered really whether this was true and whether the practical and ethical challenges that arise by using this deception are worth it. As will also become visible, evident in the next few slides, and Emily touched on this as well in her talk just now, we can also use these manipulations to try and tease apart the social specificity of the mechanisms that underlie social interactions. But as time has gone on, I've really appreciated the importance of these manipulations and this question for understanding how these expectations and beliefs change the way we perceive and interact with other artificial agents. So if you cast your mind back to the burglar task with Alan that I talked about before, in our initial studies using this paradigm, we came across an interesting pattern of initiating behavior that participants exhibited across several studies. And so in this task, when participants find the burglar, they're actually required to look back at Alan, establish eye contact, and once mutual eye contact is reciprocated, they can look back at the target to achieve joint attention. Likewise, in the non-social task, when they find the burglar, they look back at a central fixation point, they have to wait for that to turn green, and then they look back at the burglar to catch the burglar on their own. And what we found was that participants showed this behavior where they would sort of dwell on the burglar when they found the burglar and were hesitant to look back at Alan to establish eye contact in the social condition. And if they did, they engaged in these premature saccades back to the burglar to initiate joint attention without patiently waiting for Alan to reciprocate eye contact. Whereas in the non-social condition, participants were much better at quickly looking back at the fixation point, waiting for that to turn green and looking back at the target. And so one of the reasons for this was I didn't expect this to be the case because I thought establishing eye contact in this context is really important for conveying your communicative intent with your partner. But it occurred to me that this makes sense in the sense that in everyday interactions, we don't explicitly make eye contact with people as a strategy. We look at things and we use other cues and we expect our partner to be motivated enough and intelligent enough to follow our attention and look where we're looking. And so I thought, well, a great way to test this hypothesis is to see if people do the same thing when they don't believe they're interacting with a human and when they believe they're interacting with a computer. And it turns out they don't. So when people believe they're interacting with a computer, they don't display this behavior and their performance is commensurate across the social and the non-social conditions for both of these measures of initiating behavior. This was also matched with differences in some subjective experiences during the task. So people who believe they're interacting with a human found the task less intuitive because Alan wasn't behaving how they would expect a human to behave. But despite this, they found the task more pleasant and more cooperative and the interaction more cooperative than those in the computer belief condition. So there's something very forgiving about believing that you're interacting with an intelligent agent, in this case, a human. And so we can understand this behavior in the context of Daniel Dennett's intentional stance framework. So when we believe we're interacting with Alan the human, we adopt an intentional stance and our behaviors are guided by assumptions that we make about Alan's intentions, his intelligence, his beliefs, and his rationality and motivation. So Alan is motivated to respond and he's smart enough to respond. I don't have to make explicit eye contact with him. But when we believe Alan is a computer, we adopt a design stance, and we engage in the task from the very beginning, making assumptions, assuming that there's some sort of mechanism at play that we need to figure out how it works and hack this mechanism. So participants engage in the task from the outset, trying to figure out what they need to do to make Alan respond to them. And so they find the task more intuitive as a result in this context. So you can see how our expectations about what these agents are capable of shapes how our behaviors that we use to engage and coordinate with them. And so the final series of studies I want to show you is a similar paradigm that we used in an ERP experiment, where in this task, participants always had to initiate joint attention towards one of 4 locations. And they would then look back at Alan, and he would either respond congruently by shifting his gaze to achieve joint attention, or incongruently to avoid joint attention. And there was a whole cover story to explain why he sometimes did this. And we found that ERP's time lock to these gaze shifts differentiated these congruent and incongruent gaze shifts at a P250 and 350 interval, which we initially interpreted as reflecting the time course in which we evaluate the social significance and outcome, the social significance of gaze and the outcome of joint attention. But we could also interpret this as some non-social effect of attention or prediction error. So we thought a great way of teasing this apart would be to use a non-social condition, a conservative non-social condition, where participants interact with the exact same stimulus, but they no longer believe they're interacting with a human, and instead believe they are interacting with a computer. And we found these ERP effects to be much less reliable at the individual level and non-existent at the group level. And so, but we did find some individuals showing hints of this effect, and we hypothesized that maybe this is being driven by individual differences in our tendency to anthropomorphize, whereas when we don't believe that we're interacting with a human, but when we force people to believe they're interacting with a human, we're standardizing these tendencies to anthropomorphize because everyone is anthropomorphizing. We followed this effect up in a second study where we manipulated these beliefs within subjects, and we found that this P250 effect held true. So we saw these larger P250 responses when Alan shifted his gaze to achieve joint attention with us, but only when we believed that he was a human and not a computer. And this makes sense because you can only truly achieve joint attention with another sentient being. And we were quite compelled by this because this was true irrespective of the order in which people held these beliefs about the agent they were interacting with. But then we tempted fate and we tried to replicate this in 2 groups, again, using this within subjects design, but in 2 groups who either interacted with the same stimulus or a mecha robot face stimulus. And to our surprise, we actually found that the stimulus didn't matter so much, but these intentional stance effects were less reliable than we thought at the individual level. But what was reliable were these congruency effects. And this time we did have data on individual differences in anthropomorphism. And so we had a look at the size of the congruency effect when people believe they were interacting with a computer. So they don't explicitly believe they're interacting with a human. And we found here that the size of the congruency effect was correlated with their disposition to anthropomorphize. However, this is highly tentative data, and there are problems with how we measure anthropomorphism, but I think this is a really promising avenue for future research and further factors that we can explore when looking at the factors that influence how we process social information with other agents, whether they be human or non-human. And I think there's lots of work to be done at also looking at differences not only in whether we manipulate intentional stance as human versus computer, but different types of computers. So intelligent artificial agents and maybe less intelligent artificial agents. So I'll finish there, and thank you for your attention, and thank you for all the people who've contributed over the years. Thank you.
Well, thank you so much, Nathan. That was really interesting, and still I need to have some more time to digest your findings. If you can unshare your screen, then we can see you in full glory. Wonderful. Yeah, I'm working and thinking about the perceptual co-representation in right now on human and robot and human. So that is super relevant for me and really interesting. So thank you for that great talk. I'll just directly move into questions that we had in chat. What is the type of information that we receive from the other's eyes? The fact that they are thinking about an object, are aware of an object, are communicating something to us, or all of the above?
I think all of the above. And but I think the problem with a lot of the previous research and mine included is that when there's only eye movements available to us, it's very difficult to figure out what these eye movements mean. And so that's why in our previous research, we had this real emphasis on almost forcing participants to make eye contact before initiating and responding to a joint attention beat, because in this deprived form of social communication, it's your only way of saying, differentiating whether an eye movement is non-communicative and searching an environment or communicative. And so that's not the case in realistic face-to-face interactions where we actually use other gestures like hand pointing gestures, but there's also context. So if we're talking about a dog and there's a dog nearby and I quickly look at a tree, the tree is that gaze shift, we immediately disregard that gaze shift as being less relevant to the conversation being had. And so I think it can mean all of these things, but it depends on the context.
Okay, wonderful. Then I think we can directly jump into the next question. In the numbered blocks coordination game, do you think people would perform worse if they didn't see each other's eyes?
I think not necessarily. I think what the eyes present is, I think there's a trade-off, a computational trade-off. So if the eyes are reliably providing congruent and predictive information, then it does take more social cognitive computational processing to attend to both of those cues and to integrate those cues, but it will make you faster if the gaze information is reliable. If it's not reliable, though, it's a much better strategy to actually ignore the eyes completely, ignore the face completely, and just follow the hand cues. It might make you slower overall, but you'll be using less, it'll be less computationally demanding. And so we're actually in the middle of running a study with autistic teenagers who are doing the same task, but with this confederate setup. And in this task, the confederate's gaze is congruent on half the trials for all of the participants. And so here there is sometimes an advantage and sometimes not an advantage for using gaze. And what we find in our autistic participants so far is that they attend less to the gaze information of their partner, but overall, they're actually trending slightly faster in responding to the gaze cues because there is not a net advantage for using gaze in that context because gaze is not more reliable than unreliable in that case, if that makes sense. So I think, again, it depends on the context and it depends on whether the gaze information is reliable in the first place.
Yeah, that's super exciting and interesting to hear. I mean, going into VR, that's another kind of very interesting topic where you have avatars, right? And then you have a direct influence on how they interact with you, and seeing that it is context dependent might give you really some insights in how you should design them in the first place.
Yeah, exactly.
Wonderful. With that, thank you much for joining us for Australia. We kind of ran out of time, and yeah, thank you again for that great talk and for giving the talk at that late hour for you. For us, it's great. Yes, a pleasure. And we have for people who are joining us not so late, we have our lunch break, and we have set up a social interaction gather town where you can join in and chat with our speakers. So please feel free to jump right in there. It should be in the live stream chat and available on the website as well. Otherwise, thank you all for participating, for the great questions, for the great talks we had so far. We will continue at, let me check, 1:30, so in an hour, with a couple of native speakers, Stefan Kopp and Ruud and Nicolo, who will continue that trend and disciplinary discussions we had. So with that, thank you again to our speaker, and see you all later today.
Hi.
Hello, how are you?
You all right?
This week is mad. I don't know, everything is piled up, but I don't feel I can complain because you've
It
been
will be
doing
great. Don't worry.
enormous.
We are live we're live now, and so in 4 minutes we'll start. We've set up our next speaker. I'll just introduce everybody. So welcome back to everybody who's joining us a little bit early. We will be starting punctually in about 4 minutes time with our next speaker, and we have, as ever, a very exciting lineup for you today. We very much hope that you will enjoy what we've prepared. We have Stefan Kopp talking first today from Uni Bielefeld, followed by Ruth Hortensius and Nicola Piscitelli. So we have a European contingent after an Antipodean one. We very much hope that we have prepared a nice variety for people. We'll be looking at artificial social intelligence for truly cooperative human-agent interaction rather than just only seeing the bad side of AI. We've got a nice focused one on social interactions and social cognitions that might mimic or shape how we design robot everyday interactions. And indeed, what happens when we have hybrid groups. So we have a nice mix, and chairing today will be the irreplaceable, the wonderful Ophelia de Roy. So we thank her for joining us today, a co-organizer of this event, and I'm so grateful to see your lovely face. And yes, so we very much look forward to what we have on offer today. I'm trying to quickly open up our website so that I can once again just show you indeed what you can do there. We have Stefan Kopp entering as we speak.
Wonderful.
But yes, very briefly, you can access our program at any time, and it's here really that you'll be able to get any of the extra information that you might be missing. You can access speaker information and their abstract by simply clicking on the relevant details here. We will have another coffee break where we can gather in our Gather Town space. I hope you'll join us there to make up for any missing social interaction that you may be having at this time. But also, please don't forget to engage either on our whiteboard, which you'll find here, or indeed on our live chat. Please, the beauty of this is that we can, in fact, feel close even though we are far. And indeed, without further ado, we have got Stefan Kopp in the wing. Hello, Stefan. Can you hear us?
Stefan.
Hello, nice to meet you.
Perfect, thank you. And Stefan, as I said, Ophelia de Roy will be chairing this session, so I'll hand over to Ophelia. Ophelia, you are in charge.
Excellent. Thanks, Stefan, for joining, and welcome everyone for this session. So we'll be hearing from our speaker about truly cooperative artificial intelligence. So we are looking forward to your talk, and the floor is yours. The virtual floor.
Thank you very much. So you can see my my slides, everything all right? Thank you very much. Yeah, thanks. It's a pleasure to be here and to join this exciting conference, which is addressing, I think, a very important topic these days. So I'm going to talk about artificial social intelligence for truly cooperative human-agent interaction. And I would like to start by talking about, okay, so where are actually we heading in the field of human-computer interaction? So since the last, let's say, decade, there is more and more like mentioning of, okay, where is the field heading? How is the interaction between intelligence systems in particular and human users are going to be structured or conceived in the future? And like even our Federal Ministry of Research once said that, okay, now it's important to make the technology to make it, like, become a partner of the humans. So it's moving from designing technical systems as merely tools to to what actually. So we see a lot of like different concepts popping up here. So we all, of course, we all know personal cognitive assistants like, that are mainly characterized by the ability to interact through natural language dialogue and map like user requests onto certain like back-end services and provide information and so on and so forth. We also have an increasing number of robot assistants, especially mobile robot assistants in different environments, for instance, household environments like the Care robot here, or even the International Space Station, like the Simon robot that was up there in space. And then in the, especially in the manufacturing industrial sector, we see more and more collaborative robots that are supposed to work together in the vicinity of people, actually. So, but what actually is this kind of interaction then? So how is it structured and organized? And if we look at what human-robot interaction, how it was conceived like 15 years ago, then we see like this development from, okay, so the contact with humans is closer, more closely, it's over a longer period of time, it's shaped by learning, it's open and it's adaptive, it's not so much shaped by clear roles and clear functionalities and responsibilities of the system. And also the role of the robot is moving from tools to assistant companions or partners, something like that. And that also requires those systems not to be like super capable in terms of fulfilling their physical tasks, what they are designed for in the first place, of course, but also to be able to interact socially. And these social skills are being more and more essential. So what actually is it to collaborate? And so what does it mean to collaborate? And if we look back at, for instance, literature in philosophy and psychology, and it also was very much inspiring the early work in AI on collaborative agents, for instance, by Barbara Grosch and Candy Seidner and people. Then they all share this view, okay, that what's really a shared collaborative activity, so really a cooperation and collaboration between two or more like autonomous agents is, so both are having a joint goal and they are committed to fulfilling it. And they're also committed to mutually support each other in doing so. They have this joint plan, so they're both aware of their joint goal, but also aware of their joint plan to achieve it, which includes like meshed sub-plans and also individual responsibilities. But they also collaborate closely, and they are willing to coordinate both during deciding who is going to be in charge of what, and then also while doing so. And this is like a continuous coordination process that needs to like go on and be continued throughout the whole interaction. So in the early days of AI, let's say in the early days of collaborative agents in the 90s, so people started out by explicitly modeling this kind of like framework in terms of shared plans. So it seems natural to start to pick up from this like existing symbolic approaches to planning and to reasoning and inference and logic-based representations, and then to extend it to this domain of collaboration. So then we had like shared plans, and it was like an inferential problem basically to come up with those, and a search problem to come up with those plans. And it's important though that that there is this sharedness to these plans. So that means both agents in this case, so let's assume we have only two agents collaborating or cooperating, both agents need to be aware of this shared plan, and they need to be aware of the fact that the other one is also aware of it. So what really is needed is what I would like to call artificial social intelligence, and it obviously goes back to the classical notion of social intelligence or interpersonal or interactional intelligence, and that basically is the ability of us humans in the first place to be sensitive to one another, to moods, feelings, but also to beliefs, to epistemic states, but also to intentional states, goals, desires, and so on and so forth. And it's like the basis for being able to cooperate and communicate with each other. And there is a lot of different abilities that nowadays are being considered and researched in the field of, for instance, social cognitive neuroscience or social psychology or cognitive science more generally, as well as increasingly now AI and human agent and human computer interaction. And it involves, for instance, being able to process the emotions, to track intentions, to track attention and establish shared or joint attention, to predict behavior, to distinguish between one and other in terms of who knows what and who wants what and those things. But this is still far from being reached, actually. And most often those things are not being considered appropriately, I think, in current attempts. So there's a lot of research challenges still there. And one that, for instance, the field of social signal processing or now social behavior processing has been tackling is to be able to understand agents and their subtle cues, and to be able to interpret their behavior in terms of some mental states like affect, certainty, competence, something like this, for instance. But understanding social situations and agents is only the one part of it. It's also really important to be able to produce social cues, for instance, and to engage in this ongoing communicative process between agents, right? So it is an incremental and closed loop that we are interacting with each other. And it's framed by and it's shaped by an inter-agent interaction dynamic process, which in itself is rooted in what each and every agent personally wants, believes, is assuming about the other one, and decides to do. And all of this is framed in what's often called context, but I think it can be differentiated a little bit further into, for instance, the social expectations, the norms, and also the kind of relationships that hold in those human-agent interaction encounters. And if you look, for instance, in human-robot interaction and social robotics more generally, this is really what people are starting to look at more and more closely nowadays. So in the reminder of this talk, I just want to report on 2 examples of the various research projects that we are running in this direction. And one is here on the left-hand side, to be able to do what we call online mentalizing. So that means being able to understand the mental state of my cooperation or interaction partner, in this case, the human user, and to infer it and to predict it, and then to leverage that kind of modeling and that ability in order to improve communication in term with regard to its, for instance, efficiency and robustness. And the second example I would like to tell you about is like the other way around. So how could the robot itself shape the understanding of the user of the robot? So that the mental model that the user is building and holding about the robot. And one particular really interesting example of that is through explanations. So let's start and let's look at the first one, employing online mentalizing for adaptive efficient communication. So one thing that people have been working on a lot and that has really like advanced a lot in the last decades through the means of a lot of data and machine learning techniques, deep learning, and especially is the ability to interpret basically signals and patterns, also behavioral signals and patterns, and also social signals and patterns and behaviors. And that has really like shaped and spurred this field of social signal, social behavior processing. And we did the same thing here. So we wanted to be able to recognize from, in this case, for instance, visual input, so facial features, as well as auditory acoustic features about this from speech of the user. And we wanted to be able to recognize not just emotions, but really interaction-related mental states. And we were in particular interested in, does the user agree or disagree with what the robot is doing or saying? On the one hand, on the other hand, is the user confused? So does the user understand, basically, right? And well, how you do it, so you get a lot of data and you train a big neural network, and then actually you get quite good results nowadays. And here, for instance, we see an example of a system that is able to estimate in real time the agreement and confusion of the user from 2 kinds of input, again, facial features and only acoustic features from the speech. So it's only like intonation, prosody, it's not like linguistic features, for instance.
I am going to now pick one of the 12 cards. Okay, I picked a card. You can now ask me yes or no questions to find out which card I had picked. It's not 12 cards. So... okay.
So what you can see is that the system is able to continuously assess the confusion. That's the bottom, the graph here at the plot at the bottom. The confusion as well as the disagreement and agreement, and they are continuously fluctuating. So this is just an example of what many people in the field are nowadays working on and what we are like able to do, basically. But the key question, though, that is less answered, I think, is okay, what to do with it now. So if they're able to let's say to recognize the users being confused, so what to do about it? So how should the system actually respond to it? And this actually is a way harder problem. And this is something that we look at together with my PhD student and then postdoc Henrik Buschmeier, for instance. So the thing is, where if you look at dialogue, for instance, then there's a lot of social signals that not only the speaker actually produces all the time, but also, of course, the listener, the addressee, is producing back. Sometimes those have been called back channels. And this is something that are actually turn out to be very, very important important. So there are a lot of social signals that even speakers, while they are speaking, are producing, basically, are responding and reacting to, and those cues and feedback signals that are being produced by the listener, by the addressee. Yeah. So, for instance, a user might tell, in this case, the virtual avatar, okay, then tomorrow, then the agent got it and says, mm-hmm. And this is signaling to the user, okay, so until now the system understands me well, and I can just continue. And I would say, okay, and then I can continue saying, I'd like to visit my friend Mark, for instance, right? Then finally the agent acknowledges and says, okay, and nods with the head, and this is fine. In linguistic and dialogue theory, this is called like grounding process, and there is different kinds of like signals that, for instance, in this case, the listener, in this case, the agent, can produce in order to signal understanding to the speaker, right? So we know that listeners provide feedback, and they actually do so in a quite sensible way. They produce feedback that is also informative, that is communicative even, and they do so in order to stabilize the dialogue and to enable to project their level of understanding and to make it transparent to the speaker, basically. And this has been done in dialogue agents as well. So a lot of so-called attentive listening systems have been developed. So, but we look at the opposite direction. So if the agent is like delivering, providing information to the user, let's say, for instance, reminding the user of a certain appointment or making a suggestion for when a certain appointment should be made. So let's say at 8 a.m., okay, and the user says, and maybe like also like twist the head a little bit. This is also an indication of the agent who might be able to infer, okay, he doesn't seem to agree, so I would rather go and maybe suggest like a later time, for instance. So this is what we would call attentive speakers, and that means attentive speakers, and this is at the heart of communication, and in this case dialogue, is cooperation as well. So they should cooperatively respond to, take note of, and respond to these communicative feedback signals produced by listeners. To that end, they need to be able to understand them in terms of interpreting the mental state of the listener. So is the listener, is my addressee, my communication partner, is she signaling she is not able to understand me, maybe perceptually, acoustically, or semantically in terms of content? She doesn't know what I would like to really want from her, like in terms of pragmatic understanding and intentions, for instance, or she doesn't agree, or she doesn't like what I'm saying, and so on and so forth. So there's different kinds of functions that listeners, in this case, can try to fulfill through their communicative feedback. Speakers, in turn, need to be able to understand and interpret it in order then to be able to change their behavior, and as fast as possible. And it turns out that speakers do so, and even if they are, and they actually are, they need to be able to predict and to maintain a model of the mental state of their interaction partner. And if they don't get information back from the listeners in terms, for instance, like feedback, then you can even find them to elicit it by asking, are you with me? Do you understand? And those things. There's actually cues that people can produce. So what we did here was exactly this. So it's not just that we would like to understand and to be able to recognize confusion or agreement. We need to know what kind of specific feedback function actually is that the listener, through her feedback signals, would like to convey to me now, right? We call it attributed listener state and treat it as the Bayesian inference problem, right? So you get information about, like sensory information about facial expressions, head movements, prosodic and paraverbal information like or and then you interpret it in terms of, okay, the addressee is signaling he is in contact and he's perceiving me, but he is not understanding what I'm saying in terms of meaning, for instance, okay? So if we have this, then we can then actually start to adapt the running behavior to it. So we built a system that is then, while actually producing and explaining something to the user, at the same time attending to the feedback of the user and then responding to it by way of adapting its own natural language generation, for instance. And here's an example how this works. In this case, the user signals understanding. Okay, so the user acknowledges it with some and also nods with the head. So then what you see at the top of the movie here is basically how this probability mass in this probabilistic model basically shifts to the right, which means the agent is certain that the user is understanding. So that kind of model allows the system to understand and interpret the user, the feedback of the user in terms of the mental state of the user, always with respect to interaction relevant mental states, but also to, for instance, to proactively elicit feedback if the agent is too uncertain about it, which can be nicely directly implemented in those kinds of probabilistic models, for instance. Okay, so we actually applied it in real human-agent interaction, for instance, and we really find that with participants that people actually are intuitively producing feedback to such a human-like anthropomorphic virtual character, only presented on a screen in front of them and explaining them what they are supposed to learn about and to remember as part of this experimental setting. They also produce more feedback if they note that their agent is attending to it, so responding to the feedback. They rate this attentive agent more positively. In the end, the whole interaction is becoming more robust and more efficient, because if we define efficiency in terms of how much the participant understood minus how long, for instance, the interaction was, so interaction cost, for instance, then it seems like this kind of more or less implicit coordination plus the social mentalizing capability behind it actually helps to like find a very efficient dialogue. Okay, finally, the second example I'd like to talk to you about is the other way around. Namely how a robot can shape the user's understanding through providing self-explanations. So explaining explainability AI, transparency is like a big thing these days, and it's extremely important and a very big challenge for many AI researchers, of course, right? And also for robots and interactive agents and human-robot interaction, for instance. And people have been now like stating that a robot, for instance, should really have solid access to its own reasoning in order to be able to provide a comprehensible explanation of it to a human user, right? So here, what we did, for instance, here is, so we looked at what we might call a social companion robot for the household scenario, household environment, for instance, right? So in that situations, it will often happen that the robot will produce some surprising and also some less desirable behavior. For instance, like here. So the user is watching TV and the robot is just like driving in front of the TV and looking at the user, right? So the question is, okay, how would the user try to make sense of it, especially in a way that maybe might, for instance, let's say, restore, let's say, acceptance or trust, and also, or at least might help the user to understand what's going on in the robot, maybe in order to adjust the behavior of a robot. So for instance, you could then, of course, user might be able to say, okay, so Paper, can you please explain your behavior? And then the robot might say, I intended to contact because I needed social contact. So because I needed social contact. So now you see the robot can, of course, provide different kinds of explanations here, right? So the robot people have been proposing that the kind of explanation that you should and could provide very dramatically with, for instance, the kind of behavior that you've shown, the intentionality of the behavior, how surprising it was, and also how socially desirable it was. So we designed different kinds of scenes that might occur in such a with such a social companion robot, where the robot produces behavior that is more or less surprising and also more or less desirable, for instance, right? So here, for instance, you see an example. So the robot, the user wants to leave the, let's say, the living room, but the robot is constantly moving in front of the user and blocking the way, basically. Or here another example. So the user wants to enjoy some music, and then the robot all of a sudden also tries to play some music and so forth. So how should the robot explain this behavior, and what kind of explanations actually would be helpful from the user's point of view in terms of enabling the user to understand the behavior and maybe also to accept the behavior? And this is something that we wanted to know. And this actually goes deeper. So the deeper underlying, of course, like theoretical background of this is, okay, how should the robot present itself to the user, or the other way around? What kind of mental model should the user have and hold for the robot? For instance, in terms of should the user look at the robot as an intentional agent, whose behavior maybe rests on principles like desires, needs, and intentions, or that would be like called intentional stance, for instance. Or should the user maybe like take a more like a design or physical stance throughout the robot and just look at it as if it were just like a stupid machines and it's all like automatic and not autonomous behavior, for instance, right? So we presented human participants in the study with different kinds of explanations. So, for instance, one explanation where the paper just basically merely states what it did. I played a song. That's all. It could also, for instance, pretend it had attention and say something like this. I intended to enjoy some music. It could also provide, of course, like a combined explanation by saying, I played a song because I intended to enjoy some music. So providing some causality and cause and reasons basically for its behavior. It could even go on, and this would be what you see here. So the one scale that we would call agentive explanation, the one would be causal explanations, and increasing the agentive explanation scale here would mean the robot might, for instance, state it had a need or desire to do something. I needed entertainment, and that's why I played music. And this is like intention plus need combined explanation. So we presented this kind of different explanations to participants in the study, and we found, first of all, although the behaviors that we showed them are really often not well understandable and really surprising, and that we control for a pre-study. All of the behaviors, regardless of what kind of behavior the robot gave, they all improve the understandability of the behavior. So what you see here is a pre and post comparison. Pre is blue and post is the purple bar here. And for each and every behavior, you see the purple bar is basically bigger than the blue bar, right? We also found that the highest understandability gain were achieved by providing causal explanation. So saying, this was my action and I did it because I had this intention, or I did it, that was my intention and I had it because I needed this and that, for instance. In terms of desirability, we find a similar pattern. Participants find behaviors really more desirable after receiving an explanation. And recall, most of those behaviors are really not socially desirable, right? At least they are sort of like disturbing for the user. Again, we found highest desirability gains with those causal explanations. And interestingly, though, here on the left-hand side, you see actually no difference between the blue and the purple bar. And that means the needs-based explanation. So just saying I needed social contact didn't help at all. So this was maybe like too far away on this axis of like agentive explanation for users. Okay, so to conclude, for human agent cooperation, it really requires a certain degree of mutual understanding and coordination. And people have been looking at it a lot, and we are still doing it. And I think we even need to do it more these days when, for instance, cobots, collaborative robots, and like social companion robots or cognitive systems are becoming more and more commonplace, obviously. We have to work towards what I like to call artificial social intelligence. So that means we have to complement the task intelligence and the task abilities of those systems with abilities for not just communication, but also cooperation. So understanding other agents, users, their tasks, their mental states, and also be able to like do some relational or social planning that takes those into account when producing system behavior. Of course, those tasks are really, really complex cognitively and mentally, but I think we can really leverage on the incremental nature of interactive encounters by saying, okay, all we do is now we go for an adaptive, let's say, good enough processing style, but then being attentive and responsive to the interaction and being attentive to and responsive to the signals that I'm getting back from my interaction partner, right? So in the end, thus, we need to develop AI models that ground interactive behavior processing in the dynamic social cognitive processing and also vice versa. And with this, I would like to thank you for your attention.
Great, thank you so much, and a lovely, quite impressive performance on the side of the AI, I have to say. We have currently already 2 questions, and one is coming from Jurgis about the first part of your talk, and asking actually how the communication cues that the AI is picking up on for the confusion, agreement, and disagreement, how similar they are across cultures and across formal and informal settings. So did you measure this, or?
No, we didn't measure this. Of course, there's a vast body of literature on that. Like, for instance, emotions that have been usually looked at being universal to some extent. But I think it's really important to note, of course, there are universal components to it, to the social signals, of course. And of course, if we go to a foreign country, and then we quite readily note it. But at the same time, I think it's really important to note that there are huge individual differences already between people, personalities, speakers, listeners, and so on and so forth. And it's therefore also so important actually to be like adaptive to it, right? To be able to basically to adapt on the spot, basically, to my specific interaction partner. And this is something that our like AI systems and the way we used to build them these days actually I have a hard time basically like coping with, right? Because what we do is we learn models from tons of data and basically ending up with averages and mean values, basically, right? Yeah.
Great, that's the and the second question that we have time to squeeze in on the second part of the project was about the choice of explanations and whether it could make sense for the AI to select manipulative of not truthful explanation in order to satisfy the user, and whether that's possibly problematic. So whether you see a tension between being truthful and being efficient socially.
Oh yeah, absolutely. Of course, there's a big tension, of course, and we really have to be aware of this. And I think I must say, we are aware of this, and people are increasingly aware of this. You know, there's big concern about ethical AI and ethically responsibly aligned AI and so on and so forth, right? Especially here in this regard, that's of course true. On the other hand, though, I think it's important to note that, so for instance, in human-computer interaction, we used to design interfaces such that they present, so that the system is being presented in a certain way to the user in order to be, let's say, cognitively ergonomic, right? So understandable, predictable, and so on and so forth, right? That needs to be truthful, of course, but that is always, of course, like reducing information to like a bearable amount, for instance, right? So it's always a matter of leaving out information and giving information. But of course, it needs to be, I mean, we need to make sure
non-manipulative
that
in that
getting the true information. Yeah.
Great, thanks. This is all we have time for to keep on time with the planning, but thank you so much, and people can check the recent papers of your lab and all the amazing things you have developed. So thank you so much, Stefan, and
thank you.
See you. Bye. So I think we have.
And also for me, thank you so much, Stefan. And we have our next speaker, Ruud Hortensius, joining us in the wings.
Yeah, I will join and watch the talk via YouTube, right?
Thank you so much, Stefan. See you.
Yes.
See you.
Bye-bye.
Great.
See you.
Okay, thanks. Bye. we have
Yes, our next speaker is waiting. Ruud, would you like to switch on your camera so we can see you?
Yeah.
Great, thank you.
excellent. So we are perfectly on time, which is great, and it's a great pleasure. Do you want to share your slides already, Rod? Maybe.
Yeah.
Or
yeah.
next.
So you should.
Speaker.
Yeah.
Yeah. Perfect. We're seeing you, and without further ado, to give you the stage very quickly, we'll listen to Rod Hortensius from Utrecht. Again, more on social interactions and social cognition. So that's great for today's topic. Thanks.
All right. Thank you so much. Well, thank you for inviting me and giving me this opportunity to present some of my research at this great conference. It feels good to be among friends and colleagues in the field. So my name is indeed Rud Hortensius. I'm an assistant professor from Utrecht University. And today I want to talk about how real interactions with robots shape everyday social cognition. And when I was preparing for this talk, I went back to look up the source of one of the pictures that I use during this talk. So I use Unsplash, which is a great database for photos. And in Unsplash, I searched for social interaction. And then I got this picture. So these are people having a coffee in a cafe. But these are just not only people in a coffee shop, because we can already see the near future of AI in this picture, right? Like, so a lot of people are using phones and other like smart technologies. So we can state that the near future is already here. So technologies are everywhere. So I think it's critical to investigate the impact of our social lives, the impact of technology on our social lives. So something that I term contemporary social cognition. So understanding social cognition in this new light, in this era of technology. For example, since I'm interested in human-robot interaction, I want to know, when do you see a robot as a machine and when do you see it as a social being? What are the brain regions that are activated during these interactions with social robots? So really, in order to understand the impact of a human-robot interaction on different aspects of social cognition, we need not only to look at perception, but also real interactions. And I think, like, in keeping with the theme of this conference and the great talks by Antonia Hamilton and Emily Cross, who already showed that movies and other sources of entertainment and the arts can be a great source of inspiration, I highlight some of scenarios from a great movie, Robot and Frank, that will already give us a great way of dissecting social cognition. So with new technology, you can actually ask these questions on what the impact of social robots are, what the impact of social robots is on social cognition. For example, we can ask, like, well, can you actually collaborate with a robot? As in this case, Frank is doing with the robot. Or in this case, former President Obama is interacting with a Hyundai robot. But also we can ask more complex questions on, like, how do you form relationships with a robot? As Neil deGrasse Tyson is doing at the moment with Pepper, the robot. But also we can look beyond just like these positive examples. We can also look at the negative consequences of these interactions. So, for example, there's a great scene in the movie Robot and Frank where a group of kids is actually teasing the robot. And this is not actually fiction, because there's this great paper that was presented and published at HCI a couple of years ago, where a group of children actually ganged up on this robot that was employed in the mall. So the question I'm trying to answer is, like, what factors determine the outcome of human-robot interaction? So is it the robot, is it the human, or is it just like an emerging property of the interaction? So building on previous work, I reviewed together with Emily Cross the literature, and actually we can tease apart aspects that influence a human-robot interaction.
So we can look at the cues that a robot brings to this interaction. For example, the form and movement of a robot, the presence. So is the robot actually in the same room? But also we can look at the knowledge cues, the cues that a human brings to the interaction. So beliefs and expectations, but also inter-individual differences, such as anthropomorphism, which I will talk about in the final slides of this talk. But more importantly, we can look at the interaction. So like, how does the interaction evolve over time, but also how does it change distinct aspects of social cognition? And I'm taking a neurocognitive perspective on human-robot interaction, thereby looking at distinct aspects of social cognition, focusing on emotion perception, the understanding of the intentions of other people, but also the feelings of empathy for someone else, and thereby looking at behavioral measures, but also activity inside brain networks that are foundational for these social cognitive processes. And the simple question we're trying to answer in these studies is if similar neural mechanisms are co-opted during interactions with social robots, as with fellow humans. So in the first study, I want to explore the limit of human social cognition by testing the flexibility of empathy, thereby allowing to answer the question if a potential human bias in social cognition is the result of a phylogenetic evolution, or does it have an ontogenetic origin? So is it because of learning and experience? So empathy for robots, you might say, like, well, this is a bit far-fetched, isn't it? But actually, we know from studies done by Julie Carpenter that even soldiers that are using bomb diffusing robots, they can feel a range of emotions ranging all the way to empathy. Because if a robot is destroyed, they will actually hold funerals for these robots. They attribute all these human or animal-like attributes to these bomb diffusing robots. If a bomb diffusing robot is destroyed, they want the same robot back, even though it's destroyed. So already that gives an insight that maybe spending some time with a robot would actually influence feelings of empathy towards this robot. So this is the question we set out to answer in this study. And Emily already provided a pitch for this study. So I can just give you the details of this study. So the question we're trying to answer, if a 5-day socializing intervention with a robot would actually lead to more overlap in neural mechanisms when you observe this robot in pain as when you would observe a human in pain. So basically, we're inviting people to the lab, scan their brains, present them with a robot that they will take home for 5 days, and then would scan their brains again. So we use a technique called repetition suppression, and I won't go into detail, but the main thing to know is that it allows you to study neural overlap of similar and dissimilar categories. For example, in this case, robot and human. So we had this little robot called Cosmo that would allow participants to have either free human-robot interaction. So in this case, the robot is recognizing the student, Veronica, or you would engage in human-robot interaction, for example, playing games, thereby allowing you to form a bond over the course of 5 days. And so importantly, these interactions would take place at the home of a participant. But you can also observe the behavior of a robot on its own. So the Cosmo robot is triggered by internally and externally events. It has a frustration engine, so it becomes very frustrated if you don't interact with it for a longer time. But this allows us to really explore how real interactions with a robot would influence feelings of empathy at the level of the brain, but also behavior. So to give a more detailed overview, we're interested in to see if after the 5-day interaction, the overlap in the pain matrix, which is a network important for when you observe other people's distress, becomes activated. If overlap in this brain region, these brain regions, would increase post-socializing. So this is a bit of a complex graph, But the important take-home message is that, like, pre-socializing would expect that observing a human in pain and a robot in pain would lead to dissimilar neural patterns, but after spending 5 days interacting with this robot would increase the overlap. So what we did is we recorded videos of a person experiencing pain or pleasure and a robot experiencing pain or pleasure. So this is an actress. The stimulation is not real, but it will give you a good idea of what the participants viewed. And we created similar videos for the Cosmo robot. And so then the question we're trying to answer is, well, does this actually, these 5 days of spending interacting with this Cosmo robot, does it actually increase the overlap in neural activity when you observe this robot in pain? And as the slide already, the title of the slide already gives it away, there's no overlap in neural mechanisms of empathy after spending 5 days interacting with this robot. So this graph shows negative values would indicate less overlap post-socializing. So this is not something we would expect. Positive values indicate more overlap post-socializing. And what we see is for these two regions in the pain matrix, we see that there's absolutely no effect. So spending 5 days interacting with a robot does not lead to more overlap in terms of neural mechanisms when observing this robot in pain. If we look at across the 7 regions of the pain matrix, we don't see effect of socializing with a robot whatsoever. So we can conclude from this study is that, well, the socializing intervention did not lead to an increase in neural overlap. Of course, we also looked at subjective experience. So, for example, maybe you feel more feelings of empathy towards the robot after spending 5 days interacting with it. So negative values indicate the videos as experienced as more painful. Positive values indicate as pleasurable. So as you can see, human pain videos and human pleasure videos are rated as such. Similarly, albeit a little bit less, are the robot in pain videos and the robot pleasure videos. So we see distinct categories, but the important question is, does this increase, right? Like, does the rating of robot in pain become stronger after this 5-day interaction? And actually, this is not the case. So we don't see an effect on subjective ratings of robotic in pain or pleasure. We don't see an effect of socializing with this robot. Right, so we can conclude, well, flexibility of social cognition, well, maybe empathy is a bit too far. There's no difference in empathy towards the robot after spending 5 days. So of course, one could say, well, maybe empathy is the holy grail of social cognition. So maybe we should focus on a more distinct aspect and not something that's so fuzzy. So in this next study, I did that, where I focus on the understanding of intentions and emotion of a robot. So basically, we represented people with emotional phases of a human, emotional phases of a robot. Similarly, we presented them with a helpful or not helpful robot and asked people to indicate what the intention of the robot or human was. Thereby, trying to see if higher order networks that are important for understanding hidden intentions of other people are also activated during the perception of these intentions in a robot. And then again, asking the same question, does a 5-day interaction actually increase the overlap in terms of neural mechanisms when we're trying to understand the intentions and emotions of a robot? But first, behavioral results. So of course, what we would expect is that human emotions are recognized perfectly. So bright yellow colors indicate perfect recognition. So as you can see, there's no confusion whatsoever, pre and post socializing. However, there's some confusion for the robot emotions. So whereas sad, happy, and angry emotions are recognized perfectly, around like 100%, surprise, neutral, and fearful emotions are not recognized that well pre-socializing. However, surprised emotions of a robot are recognized better after spending 5 days interacting with this robot. Similarly, neutral expressions of the robot are recognized better, around 70%, after a 5-day interaction. Surprisingly or interestingly, fearful emotions are not recognized better after this 5-day interaction. But going back to the brain, if we contrast regions that are more activated for understanding human intentions and emotions compared to that with a robot, we don't see a widespread activation. So there's no increase in activity in higher order brain regions for human emotions or intentions compared to robot intentions and emotions. However, if we look at brain regions that are activated during the understanding of intentions and emotions of a robot compared to that of a human, we see this widespread activity in a couple of distinct brain regions. So before 5 days, after 5 days of interacting with this robot, we see that trying to understand the intentions and emotions of this robot actually activates a core set of regions that we see in different tasks as well. And one task is that of objects, like perceiving objects compared to faces and bodies. So what we can see is that trying to understand the intentions and emotions of a robot actually activates object-specific brain regions. So brain regions that are activated when we perceive and interact with objects. So together with Anna Henschel and Emily Cross, we surveyed the literature and found that actually interacting with robots consistently activate object-specific brain regions. So be it during the perception of a painful stimulus to a robot, this activates the same regions. Conversing with a robot activates part of this network, but also, as I just showed, like understanding the intentions and emotions of a robot activates these regions. And interestingly, even a simple action sequence by a toy robot activates these brain regions. So, of course, this is cutting some corners, but one could say, well, maybe robots are objects after all, or at least we should move away from human-centered brain networks and view robots as a more like neutral category. Right, so we can conclude that robots are trying to understand the intentions of the emotion of a robot consistently activates object-specific regions. So what process do we actually use when we interact or perceive robots? So when I thought about this, I remember that I visited the London Design Museum, where one of my favorite robots was on display. And this is a very simple robotic arm. But when you observe this arm, you already attribute all these intentions and emotions to this robot. And it's very simple. And actually, this reminded me of all the great Pixar movies, whereby you attribute all these intentions and emotions to these non-human agents and objects, right? So how do we actually attribute these internal states to these robots and non-human agents in general? Well, so for that, we have to take a step back and go to the foundation of social cognition and social perception. And as Friedrich Heider would say, like, well, it's all about extracting invariance out of variance. So variance is a stream of behavior or the ongoing actions of an object. And invariance is actually the hidden states, the emotions, the motives, the intentions of this agent of object. So how do we understand the mind of humans? Well, of course, we use theory of mind. So how do we understand the mind of artificial agents? Well, we use something called anthropomorphism. So anthropomorphism is attributing human-like characteristics to non-human agents and objects. And the narrative in the literature is that this is actually an analog of theory of mind. So together with Michaela Kent, who was a technician at that time and who's now a PhD student at Western University, we try to understand if these two constructs actually overlap. So we really wanted to answer the question if there's a relationship between anthropomorphism, so trying to understand the minds of artificial agents, and theory of mind, trying to understand the mind of a human. So of course, this is a very big project, so I'll only give some details of this project. So in the first experiment, we wanted to test if and how anthropomorphism is actually related to activity in the theory of mind network. So we used the Partly Cloudy movie, which is a Pixar movie where a stork is working together with a cloud delivering babies. And this consistently activates the theory of mind network. And we can actually use this to test if activity in this network is actually related to anthropomorphism. And to do this, we simply ask people to watch this movie, scan their brains, but also after this movie, complete a dispositional anthropomorphism questionnaire. So basically, we would ask them, like, for example, to what extent does the average computer have a mind on its own? And the next step is actually plotting the dispositional anthropomorphism rates for each participant and check if this is actually predictive of activity in the theory of mind network during this movie. And what we observed is that there's actually no clear relationship between dispositional anthropomorphism, so participants' tendency to ascribe non-human characteristics or human characteristics to non-human agents, and activity during this movie in the theory of mind network. So not across the network or within the regions of this network. So there's no consistent relationship. But maybe anthropomorphism allows you to understand and predict the behavior of these agents better. So that's what we did in the second question, where we look at how situational anthropomorphism predicts the ability to understand and predict the next steps of these characters. So basically, during the movie, we asked these questions. For example, does the cloud have feelings? And to what extent would you be able to predict what the cloud would do next? So maybe situational anthropomorphism would predict our ability to understand the behavior of these non-human agents. And indeed, situational anthropomorphism is related to a better understanding and ability to predict the behavior of these agents. However, dispositional anthropomorphism is not related to the ability to understand and predict the character's behavior. So, understanding the mind of a human and understanding the mind of an artificial agent are actually not overlapping constructs, but they are separate, especially at the personality level. They might be overlapping at the situational level, but only one aspect of theory of mind, because general theory of mind is not related to anthropomorphism. And there's also some dissociation between brain and behavioral measures when we look at the relationship between these two mind perception strategies. Right, so we can conclude that there's no relationship between anthropomorphism and theory of mind. So it might be a little bit more complex how we try to understand the brain, or like the minds of non-human agents and objects. Right, so how can we actually approximate human-robot interaction? Because right now these answers are really complex. So there are two strategies I foresee that will allow us to really probe the neurocognitive reality of human-robot interaction. So one is embodied interactions, so where we move away from the screen-based recordings of human-robot interactions. So, for example, how you perceive a robot. So get into, like, the first step would be these 5-day interaction studies, but really the future is using mobile neuroimaging to really understand the neurodynamics of human-robot interaction. And together with a student and Hooghuis, we are trying to explore this in more detail. So for example, we are currently completing a study where we test how humans interact and contrast this with human-robot interaction. And as you already can see, well, actually, neural patterns are strikingly overlapping or are strikingly similar. So I think like embodied interactions, real interactions, would allow us to understand the neurocognitive reality in much more detail than previously. The final thing is inter-individual and data-driven approaches. Because if we look at the individual data from these 5-day interactions, we see that there's a large variability in how and when and how long people interacted with this robot. So I think really there's a lot of ground to cover in these in the individual approaches that can tell us much more how human actually interacts with robots. Well, this will allow us to get towards a first understanding of human-robot interaction. So focusing on the brain, distinct aspects of social cognition and embodied interaction, we can actually try to understand real human-robot interaction. Or as I would say, well, maybe we should start with researcher-robot interaction, because over the course of the years, I've come across many robots, so maybe I should study myself first before diving into the real world. But without that, I want to thank you and happy to take any questions. Thanks to all my collaborators and the students involved and the funding.
Fantastic, that's great, and the new results are fascinating. I think I will actually use my chair privilege to ask the first question. So you showed that there is no such relation between, no direct overlap between anthropomorphism and theory of mind.
Yeah.
Do you think that because in anthropomorphism, we also tend to rely more on a kind of stereotype heuristics way of explaining the entities which we anthropomorphize, very template-like and not fine-grained?
Yeah. Yeah, no, that's a good question. So, in the literature, people distinguish between weak and strong forms of anthropomorphism. And maybe that's why people always thought that, well, maybe anthropomorphism is a way of theorizing about the mind of a non-human agent.
Mm-hmm.
So thereby actually using these labels that are derived from indeed stereotypes, you explain it using language that you normally use to explain behavior of humans.
But still a form of mentalizing, much more coarse-grained, in the sense that here is the nice cloud, so then the cloud will do something nice, but more character, I guess. That's okay. That's great.
Yeah.
We actually have quite a few questions on the YouTube chat for you, so I will just pick one relating also to anthropomorphism, and then you can go back to the. So we have a question from Jurgis asking whether anthropomorphism changed human behavior. Or you have anything speaking towards this, not just in the neural dimension, and if yes, is this also mediated because of ability to predict? So do you have any behavioral insight into this?
So in this study, we don't have any behavioral insight. So we asked open-ended predictions. So at one point we stopped the movie and then we asked participants to predict the outcome of the movie. And here we also see that anthropomorphism doesn't predict the actual prediction, the accuracy, nor the reliance on theory of mind. So I would argue that there's a complete uncoupling between anthropomorphism and theory of mind on one hand. So we didn't have any clear behavioral measures, but we know from the literature that anthropomorphism indeed influences behaviors towards these non-human agents.
Mm-hmm. No, it's very interesting also, because we've done also some research on anthropomorphization, not relating to robots, but it seems that it also equally explains capacity to dehumanize features. So it could be that it makes people also more resistant to any attempt to humanize the robots, which would then explain that it has no benefit in terms of theory of mind. There's so many interesting.
Yeah, so you could see dehumanization as one side of the other side of the coin, and anthropomorphism. So on one edge is anthropomorphism, the other dehumanization. Yeah.
Fantastic. I'm sorry we don't have time to read all the questions, but they're on the YouTube chat for you to check, and people can follow up about your research through your website, and you must be on Twitter as well.
Yeah, I will. Yeah, I am.
So people can follow up. Thank you so much, Fred, and great to hear your talk.
Thanks.
And I think we may have even our next speaker, Niccolò Pescetelli. Hello, Niccolò. Can you hear us? Hi, Niccolò. Can you? Yes, you're still muted. Sorry about that.
Can you hear me now?
Yes, perfectly. Great. So we're also continuing to be on time and continuing to deal with aspects of our social interactions with AI. And I think, Niccolò, are you joining us still from Berlin or?
Yeah, I'm still in
Yes. Okay, great. So we decided to start straight away without long introduction. So the floor is yours, and we'll look forward to your presentation. Thank you so much for joining.
Thank you for having me. So let me share my screen. Okay, can you see my screen? Okay.
Perfect. That's all fine. Thanks.
Perfect. So, hi everyone. Thank you so much for inviting me. It's really a pleasure to be here. I'm curious to see so many interesting speakers. So let me introduce myself. I am a research scientist in the Max Planck Institute for Human Development, as Ophelia was saying, in Berlin, where I lead the hybrid collective intelligence team at the Center for Humans and Machines. So today I will tell you a little bit about two experiments that I did in the past years that show how human and algorithmic biases tend to interact sometimes, which in turn can affect the performance of hybrid groups, which are groups that are composed of humans and machines. So in the last decade, we have seen growing concerns that the digital environment where we spend our lives may shape the information and diversity of opinions that we are exposed to, and so the perception of reality that can stems from it. So filtering algorithms, for example, search engines, ranking systems, news recommender systems, were created, with the goal to help people find what they liked in a massive landscape of information. Unfortunately, decades of research in social psychology tell us that what people like sometimes can not be good for them. So for example, in this paper that I wrote with Nick Young, I show that people seem to value agreements with other people and with the information that they consume over and beyond the accuracy that information carries. Because somehow disagreements and uncertainty are psychologically, very costly. So, what's wrong with finding information and people that tend to agree with you? Well, even if at the individual level, might not, might feel it's not a big deal. There might be problems at the population level when information across different people is aggregated together, like, for example, in democratic processes, elections, or simply when we engage in social learning, because there is a risk that reducing the diversity of information and the opinions in a group can distort our collective perception of reality and makes us victims of making correlated mistakes. So herding, groupthink, this sort of things. However, these hypotheses were never tested in the lab because they're very difficult to test. And so in this first experiment that I'm going to present today, which was recently accepted in Nature Communications, I manipulated the trait diversity of different groups and asked them under very high time pressure to search for information and news online to make a forecasting judgment about future events. So how I did this? So I asked volunteers on MTurk a large battery of questions. These were dimensions that are often used by recommendation systems online to segment users. For example, different demographics, political orientation, but also some relational and network indicators, right? So for example, I asked them about the political orientation of their average friend, as well as some personality traits that we needed for assessing, for example, their need for cognition or the famous cognitive reflection test to assess understanding of sort of system 1, system 2 thinking. And then I took this distribution of people along these many questions, and I segmented them into 3 chunks using very standard clustering algorithm. And you can see the 3 chunks here in the figure, named as core, inner, and outer segments. And what I did was take the people in the core segments, which means that they gave responses that were very close to the mean of the population. And I randomly assigned them to interact with people that were that gave similar responses to their own or more different responses. So a second dimension that was manipulated during the study was the group modularity. So when modularity was low, people interacted in one large group. So think about it as it could be like a Reddit forum. But when modularity was high, people interacted in many small groups that were kind of insulated from each other. So think about many small WhatsApp groups. And then I asked them to predict future geopolitical events, such as elections or political unrest in foreign countries. And importantly, all these problems were unknown at the time that the experiment was run. So 3 days after this initial questionnaire, participants made an individual prediction before and after they could gather information and news online on their browsers. And then they discussed all this information that they had collectively gathered in these like small groups they were assigned to, and could update their initial forecasts, as well as they were asked to make a joint forecast as a group. So 6 months later, we knew about which predictions were right, which predictions were wrong, and we could calculate the performance of our participants and of our groups. So what did I find? So first of all, when working together, people were more effective at predicting the future, right, than they were in isolation. So for example, here on the y-axis, you can see the forecasting error that was made when I aggregated these forecasts together. And you can see that the consensus forecast had a lower error than the initial forecasts. So this seems to be good news. But I also found that search engines seem to feed similar news to similar people. When you look at the forecasts that were made before online search engines were used by the participants. So here on the left-hand side of the slides, more similar people, that is like people who gave similar responses during our initial survey, did not correlate in their forecasts. So this can be seen, by on the left-hand side, the relationship between forecast correlation and the similarity between two people in our population was quite flat. But after they gathered information online, their forecasts became positively correlated, the more similar they were. So, and this, you can see it on the right as this like positive correlation that emerges between the two axes. So the algorithm that they use to gather information somehow seemed to like skew the diversity of information that people could find online and bring back to the group. Now the question is, did this affect the ability of the group to predict the future? Did they impact their accuracy? And so it did. The groups who were assigned to this high composite diversity condition tended to perform better than those that were assigned to the low composite diversity condition. Again, here I'm plotting the forecasting error on the y-axis. So lower values indicate better performance. And this is likely because larger and more diverse groups, again, with a caveat of our specific composite diversity measure, could find more and more diverse information online than more, say, homogeneous groups. But one interesting finding was that when forecasts were made and were aggregated across many small insulated groups, which is in our modular condition, this seemed to alleviate some of the problems that we found in the low composite diversity groups. Because somehow these small groups could not communicate among each other and thus could not make correlated errors. So essentially errors that were made in one group could not spill over to the others. And so when I went and aggregated these forecasts together, this improved accuracy. And this was a nice replication of a paper by Navarras and colleagues that we also replicated here. So to summarize this experiment, it looks like search engines somehow the search engines that people commonly use to search for relevant information, news, seem to feed similar information to similar people. And this, in turn, kind of negatively affected the performance that a large population of people could achieve, and the accuracy of the representation of the world that they could form. At the same time, splitting large groups into modular ones, might be hopefully like a possible intervention to avoid the risk of herding. Okay, so I want to move on to the second experiment that I will present today, because it tackles a perhaps more interesting, but I guess complementary question, which is, can the interaction of human and machine biases that we saw in the previous experiments be used to our advantage to sort of improve people's performance? And I cannot see the crowd, the people and the audience, unfortunately, but who knows what this picture represents? So,
playing AlphaGo, right?
Correct. So this is the first time that an algorithm, AlphaGo in this case, as correctly identified by Ophelia, beat a human player at the game of Go. And this, in particular, in this frame, is the reaction of Go champion Lee Sedol to this now famous AlphaGo move 37, which was the most surprising move that AlphaGo made, before beating the human champion. And AlphaGo itself calculated the chances of a human player making the same move as 1 in 10,000. So it was a very innovative move that led the machine to this kind of historical victory. And AlphaGo was able to make this move because it was not trained on human data, like many other algorithms, but it was trained by playing the game against itself. So essentially, AlphaGo could learn how to act in this problem space without being biased by how a human would play. And so this for us opened up the fascinating question, can we learn innovation from machines? And what are the limits of this hybrid social learning? So this is the work that a student in my group, Levin Brinkman, did or is doing for his PhD. And we are about to submit to Philosophical Transaction of Royal Society A. And this is what Levin did. So many decisions, including games like Go and chess, can be characterized as a sequence of states and transitions between these states. So with each action determining transition between states being associated with a reward or a loss. And so planning becomes very important if you want to maximize your long-term rewards. So for example, the last time you took a flight a long time ago, you probably had to plan your routes, and you took into account maybe information about the cost of the tickets, hours of flight, and so on. So Levin used this task by Quentin Huis and Peter Dayan, where people have to hop between nodes on a network to maximize their rewards over the course of a number of steps. So for example, here, imagine you are in Jonesville on the top left. This is a picture from leaders and colleagues. Imagine you are in Jonesville at the top left, and your task is to plan 8 moves, so to collect as many points as possible. And the points are shown in green, are the little number in green. And at the same time, you want to minimize your losses, which are like the numbers in red. So what actions would you choose? I'll give you a moment to think about it. Okay, so the correct answer is to make a loop that goes from Jonesville to Williamsville to Bakersville to Smithsville and back to Jonesville. Now, we know from past research that people tend to have what we call a loss-aversive pruning bias, which means that they stop exploring options after they encounter an initial loss, even if this is actually associated with larger rewards in the very long term. So, for example, in this case, once you get to Williamsville, it is difficult for people to consider jumping on Bakersville because this is associated with a larger cost than, for example, jumping to Brownsville. So Levin readapted this task and placed it in a transmission chain paradigm, which is a paradigm that is often used to study social learning, cultural evolution, innovation spread, and so on. And people in our experiment could replay the sequence of actions that the previous participant had chosen before they were asked to play the task themselves. And so in this way, when a good solution was discovered by one of the players, this could be imitated by the next one. And so we can assess how good solution spread from one generation to the next one. So this is an example of our control condition where 8 people are put in a transmission chain, one after the other. And you can see that the last person in the chain accrues a better score than the first one. And this is because people can benefit from what came before them. But Levin also created a hybrid chain where in the second generation, he replaced a human player with a machine player. And importantly, however, the machine was designed to show the opposite bias than humans, which means that the machine was more likely than human to explore decisions that followed a large loss. And the hypothesis was that by mixing together humans and machine with different biases and different decision strategies, this hybrid chain would do better than a chain composed of only humans, especially in those environments like the one that I was describing earlier, where humans seem to have a systematic suboptimal bias. So what did we find? First, we found an increase in the performance of the generations. And this is shown by this upper trajectory on the graph, suggesting that people were indeed benefiting from seeing the previous player answers. So on the y-axis here, you can see the performance improvement. And on the x-axis, you can see the 8 generations of a chain. The colors represent 2 different environments that we tested. One was called human rewarding, where actually human biases was adaptive to find the right solution. And one other environment, which is more interesting and corresponds to the examples I gave you earlier, called human regretful, where the human bias was actually maladaptive. And so this was the environment where we expected the machine could really show people the correct answer. So what was the effect of adding a machine to a transmission chain? So here I plot the difference in performance between the human only and the hybrid chain. So our treatment and control condition for these 2 types of environments. And you can see that there is this spike in generation 2 when the machine player was introduced. And this suggests that indeed the machine player that we added was more likely than a human to find a good solution in that specific type of environment. However, you can also see that the machine solution is quickly lost over the generations. So for example, we find a significant difference between the orange and the blue line in generation 2 and 3, but not in the following generations. So somehow people lost what they had learned from the machine. So why did the machine, objectively better solution did not stick? So in the paper, we focus on 2 possible explanations. The less optimistic one is content bias, which means that certain features of the solution simply do not stick. So for example, people might simply be resistant to copy something that goes against their inner bias. Of course, like not necessarily consciously, but they might. And the more optimistic explanation is that maybe one machine was just not enough. And being exposed to the algorithmic model multiple times is a necessary condition for hybrid social learning to occur. So to test this last hypothesis, we built a simple agent-based model where we manipulated the pruning and the copied bias of each agent so that we could model the behavior of people and machines. And we let agents learn from each other, like in our experiment. And the plot shows the rewards that the chain achieves over the different generations. So at the top, you see the orange lines. These are machine-only chains. And at the bottom, the blue lines, these are human-only chains. So in this type of environments, you see that the machines clearly outperforms the humans. Now, the green lines show the hybrid chain with only one machine among the many humans that sort of like, it's like in our behavioral data. And you can see that the pattern of results is the same, right? So this spike and then a decay, which shows that the machine benefits kind of are lost over time. However, when you add a condition where, this was not in our experiment, it was only in the simulation, but when you randomly shuffle sort of humans and machines, like perhaps in modern sort of hybrid ecologies, you can see that the red line now is in between and sort of outperforms both the human only, but also the hybrid chains with a single machine. So this suggests that perhaps the limits of hybrid social learning in these types of environments is just repetition, right? So being exposed multiple times to good solutions. So this is my second to last slide, and this is perhaps like a take-home message that I hope you get from this talk, which is I think it should be this one. So the human and machines both show different biases, either by evolution, learning, or design. And these biases can interact together in hybrid environments that we face every day. But this interaction must be taken into account when we design our digital ecosystem, because perhaps we don't feel that it affects us as an individual, but it definitely affects us as a group. So this is my last and most important slide. I've talked about many ideas in this talk. None of them would have been possible if it wasn't for these incredible people that I had the fortune to find on my path. Thank you so much for listening, and I'm looking forward to your questions.
Thank you so much, Nicolo. There are quite a few questions, and actually we have two clarification questions from Antonia Hamilton. So one, the confirmation was for the machine imitation study that you presented. Participants were told that the machine was giving the solution? Or?
No, it was completely...
Okay.
We just replayed the action, so they couldn't know if it was a machine or a human. Actually, we didn't even say that there was the possibility of a machine playing.
Okay, great. And then Antonia also was asking whether in this time the first study, the difference in the search is in the search engine itself, or in which items people choose to read from the list of 10 results?
Sorry, could you repeat?
Is the difference that people were getting from the search engine itself, or what people were choosing to read from the list of the 10 results?
In this task, we just gave the problem to solve. So, for example, what is the likelihood that there's going to be like X amount of deaths in a Houthi rebel attack by this date? Mm-hmm. So very precise questions. And we said you have the opportunity to browse the web, search for relevant information, but we didn't give any other sort of targeted advice. So they could use Google, Bing, whatever they wanted, but they had a very limited amount of time. So the time pressure was the most important.
Maybe then in the case they were phrasing the question also in the same way. That's right. I think we have time for one last question. So Jurgis, this is a big one. Jurgis was asking why you think there is a difference in the performance between modular and non-modular groups when it comes to bias predictions.
Why there is a difference between modular and non-modular?
Yeah.
So this is actually, the second axis, this modularity, was inspired by a paper in Nature of Human Behavior that came out a few years earlier by Navajas and others and colleagues. where they actually ask either like a large crowd or like the crowd was divided into these like modular groups. And there is a benefit of modularity because people can benefit from social learning, from sort of discussing the ideas and trading uncertainty within very small groups. But if they make a mistake, that mistake doesn't sort of spill over to new groups. So in a way, you maintain independence, which is super important in forecasting and aggregation, but at the same time, you benefit from others.
Yeah, that's the best of both worlds. I guess
exactly.
that's great. Nicola, there's a couple of other questions also waiting for you in the chat on the YouTube channel. So feel free to join and also in GatherTown if you want. But thank you again for this great presentation and super nice studies as always. Thank you so much.
Thank you for having me.
Thanks.
And I'll thank you also from my side. Thank you so much for joining us and Ophelia for chairing. I will just remind you all that we are very excited to have a GatherTown space for you to come and socialize. You can access that by clicking on Join Us Live and simply clicking on our gathering. You can also leave any messages or announcements. If you have a conference that you think might be related or data or a preprint, please pop it into our whiteboard. As ever, you can catch up on anything you've missed today. Hopefully you haven't. And I see that we had some really nice questions. So yeah, Nicola, if you would like to go and look at those. I will also just say thank you one more time to Ophelia for chairing the session as gracefully as always. And I look forward to seeing you all in half an hour after a quick coffee break. Go grab something yummy to eat and something to refresh. And we will see you in half an hour with our second keynote of the day from Katie Winkel. And we very much hope that we will see you then. Until then, I wish you all a happy and lovely afternoon if we will not see you again today.
Thank you so much, Merlin.
Bye-bye.
Nice to join forces on the chairing. Thank you. Bye.